Have you ever wondered how all that we see around us, the stars, the planets, even the smallest speck of dust, came from what seems to be, well, nothing? What if this so-called nothingness isn't just empty space, but a mysterious force capable of creating everything we know? Join us on an adventure into the heart of nothingness, where we'll explore mind-bending questions and theories that challenge the way we see reality. We'll journey through the origins of the universe, dive into the philosophical mysteries of existence, and explore the amazing science that fuels the endless cycles of creation in our cosmos. The scientific definition of nothing is more complex than it might initially seem. In everyday language, it often refers to the absence of things or the lack of physical objects. However, in the realm of physics and cosmology, nothing takes on a more intriguing significance. Scientists understand nothing to imply a vacuum state, a place where no particles are present, and traditional matter does not exist. Yet even in this emptiness, strange phenomena occur. In the vacuum of space, voids can still harbor energy, which is a departure from that simple definition of nothingness. Quantum mechanics reveals that even in a perfect vacuum, virtual particles can pop in and out of existence, creating moments of fleeting activity. This raises fascinating questions about the fundamental nature of reality. Is this quantum fluctuation simply a quirk of the universe, or can it be seen as evidence that nothingness is teeming with potential? Furthermore, cosmologists contemplate nothingness in the context of the universe's origins. Some theories propose that our universe emerged from a state of nothingness about 13.8 billion years ago during the Big Bang. This suggests that what we perceive as nothing is not truly devoid of existence. Rather, it is a dynamic state filled with possibilities. Hence, the transition from nothing to the cosmos has become a pivotal concept in understanding the fabric of our reality. Ultimately, the scientific exploration of nothing pushes us to reconsider the fundamental assumptions of existence. It invites us to delve deeper into the universe's mysteries, where the absence of something can reveal the presence of much more than we ever imagined. The concept of nothing is an intriguing topic that various scientific fields tackle in distinct and thought-provoking ways. In physics, particularly in cosmology, nothing often refers to the vacuum of space. At first glance, one might think of a vacuum as a complete absence of matter, but this isn't the entire story. Even in what we consider empty space, there are fluctuating energy fields and virtual particles that pop in and out of existence. This leads to fascinating implications, such as the idea that the universe could emerge from a state of nothingness, evolving from a quantum vacuum fluctuation. In philosophy, the idea of nothing is explored in depth as well. Philosophers question whether true nothingness can even exist. They delve into existential reflections about being and non-being, pondering whether nothingness can be defined or understood at all. For instance, if one claims that things can come from nothing, it raises paradoxes about causation and existence. This philosophical inquiry forces us to confront our perceptions of reality and consider how we define existence itself. In contrast, in fields like mathematics, nothing takes on a different shape. Mathematicians talk about the concept of zero, which represents a tangible absence. It's a number that denotes a lack of quantity. This abstraction opens up entire realms of mathematical thought. From the concept of zero, new ideas emerge, such as calculus and the foundations of algebra, all of which hinge on understanding that nothing can have potent implications. This stark contrast showcases how nothing can actually be something profound in mathematics. Each discipline invites us to consider nothing in diverse and complex ways, reflecting a multifaceted landscape of thought. Whether through the lens of physics, philosophy, or mathematics, the exploration of nothing challenges our understanding of existence and urges us to redefine the boundaries of our knowledge. As we reflect on these concepts, we are reminded that nothingness may not be as simple or straightforward as it appears. To grasp the role of vacuum in understanding nothingness, it's essential to start with the concept of vacuum itself. In scientific terms, a vacuum is often defined as a space devoid of matter. However, this straightforward definition doesn't quite capture the full picture or the paradox it presents. In actuality, a vacuum is not empty. It's a dynamic environment filled with fluctuating energy and virtual particles that briefly emerge and vanish. This ongoing activity challenges the very notion of nothingness. The idea of vacuum has fascinated both physicists and philosophers for centuries. In quantum physics, for instance, the vacuum state is considered the lowest energy state, yet it is teeming with possibilities. This hints at a reality that is anything but inert. Instead of merely being an empty void, a vacuum can give rise to particles and forces, demonstrating that even in what seems like nothingness, there is potential for something to emerge. This invites us to reconsider our ideas about existence and absence. Moreover, this exploration of vacuum leads to profound questions about the universe itself. The early universe, immediately following the Big Bang, was a chaotic mix of energy and particles, where even a vacuum state was teeming with activity. Understanding how this vacuum behaves under different conditions helps scientists unlock mysteries about the cosmos, such as the nature of dark energy, which is thought to drive the accelerated expansion of the universe. In this context, vacuum is not just a passive backdrop, it plays an active role in shaping the universe's evolution. Delving into the vacuum reveals that nothingness is far more complex than we might presume. It encourages us to ponder the intricate relationship between existence and non-existence, blurring the lines between what it means to be and to not be. Thus, while we often view vacuum as emptiness, it ultimately stands as a testament to the richness of the universe, teaching us that even in silence, there is a profound story waiting to be discovered. Quantum physics fundamentally reshapes our understanding of nothing in ways that may seem counterintuitive. Traditionally, when we consider nothing, we might think of a vacuum, an empty space devoid of matter. However, the world of quantum mechanics reveals that even in what we perceive as nothing, there is a vibrant and dynamic landscape. This realm is alive with fleeting particles and energy fluctuations, suggesting that true emptiness, or a complete absence of something, might be an illusion. At the quantum level, what exists in the void can be thought of as a seething ocean of potential. Particles can suddenly pop in and out of existence, creating a phenomenon known as quantum fluctuations. This means that even in a perfect vacuum, where we assume there is nothing, these energy fluctuations ripple through space. They allow virtual particles to emerge, interact for brief moments, and then vanish again. This constant activity hints at a deeper layer of reality that challenges our classical conception of empty space as simply a void. Moreover, these principles extend to our understanding of the universe itself. The universe's origins, poked by the laws of quantum mechanics, tell us that it may have emerged from a state of nothing in a very different sense. Instead of being created from a pre-existing material, the universe could have arisen from the vacuum energy of this dynamic nothingness. This concept pushes the boundaries of our understanding, suggesting that even in the absence of conventional matter, there exists a profound potential for creation and existence. As we grapple with these ideas, we are reminded that the mysteries of quantum physics continue to unfold, inviting us to reconsider fundamental concepts like nothingness. This ever-evolving picture not only opens new frontiers in science, but also ignites our imagination regarding the nature of reality itself. The journey into the heart of quantum existence is just beginning, and it prompts us to ponder what else lies hidden within the fabric of the cosmos. The concept of nothing often sparks deep philosophical discussions. In a physical sense, one might think of nothing as the absence of matter, energy, or any tangible entities. However, even the idea of nothingness can be challenging to grasp because in our universe, nothing is almost always defined in relation to something. For instance, outer space, which can seem like a void, is actually filled with cosmic radiation, magnetic fields, and the remnants of stars, so it is never truly empty. From a scientific standpoint, particularly in the realm of quantum physics, nothing is even more interesting. In this field, empty space is not truly devoid of activity. Instead, it is teeming with fluctuations and energy that can give rise to virtual particles. These particles appear and disappear so rapidly that they are difficult to detect. Therefore, what we perceive as nothing at a macroscopic level might still have an intricate and dynamic structure at a microscopic level. Philosophers have long debated the nature of absence, proposing that the existence of nothing cannot truly be sustained. In the realm of existence and the universe we inhabit, every form of emptiness is often punctuated by something else, be it energy, potential, or the laws of physics that govern the cosmos. So, when we attempt to conceive of a genuine state of nothingness, it becomes a paradox because it suggests an absence of everything, including the very foundation of existence itself. While we might aspire to imagine a physical state of absolute nothing, experience consistently shows us that such a condition cannot exist in isolation. Every concept of emptiness is intertwined with the presence of something else, making the exploration of nothing a fascinating journey into understanding the fabric of reality itself. The concept of nothing can be quite perplexing, especially when we think about it in the context of the universe. In scientific terms, nothing might refer to a vacuum, an absence of matter, or even the emptiness of space itself. Interestingly, researchers have embarked on various experiments to explore the properties of this elusive nothingness. One notable set of experiments involves studying the vacuum of space. Scientists have created incredibly low-pressure environments in laboratories, simulating space conditions. In these vacuums, researchers can observe how light behaves and how particles sometimes appear to pop into existence from nothing. This phenomenon is tied to the principles of quantum mechanics, which suggests that in certain conditions, energy fluctuations can lead to the temporary emergence of particles, giving us a glimpse of activity in an otherwise empty space. Another fascinating experiment revolves around a concept known as zero-point energy, which posits that even empty space holds a residual energy due to quantum fluctuations. To investigate this, scientists have utilized sensitive instruments, such as atomic force microscopes, to detect tiny forces arising from the vacuum. These forces are minuscule, but their implications are profound, hinting at the idea that even nothing can have energetic properties that might influence the fabric of the universe. These experiments not only deepen our understanding of what nothing truly is, but they also challenge our perceptions of reality. They reveal that what we often consider empty or void may still be teeming with hidden energy and potential, reshaping our comprehension of the cosmos. So, the next time we find ourselves pondering the concept of nothing, we should remember that it is anything but empty in the realm of science. The relationship between particles and antiparticles is indeed a captivating aspect of modern physics, and it brings us into the realm of nothingness and empty space. In the universe, every particle we know has a corresponding antiparticle. For instance, the electron, which carries a negative charge, has a positron, its antiparticle, that carries a positive charge. When these two meet, they can annihilate each other, creating energy in the form of light, specifically gamma rays. This interplay of existence and non-existence beautifully illustrates the dance of particles and antiparticles. At the most fundamental level, quantum physics suggests that our universe is not entirely empty, even in so-called nothingness. In the vacuum of space, particle-antiparticle pairs can spontaneously pop in and out of existence. This phenomenon is known as quantum fluctuations. Under normal conditions, these pairs exist for such a brief moment that they are virtually undetectable. Yet this activity showcases that even in the absence of matter, the universe is buzzing with potential, challenging our traditional notions of emptiness and absence. Now, when we think about nothingness, it can be quite a philosophical journey. Classical physics viewed space as a void, but quantum mechanics introduces a rich tapestry of activity that permeates this void. So, rather than simply a lack of substance, the vacuum of space is teeming with possibilities. These fleeting particles remind us that what we consider nothing may not be as barren as we once thought. Ultimately, the relationship between particles, antiparticles, and nothingness opens up profound questions about the very nature of the universe. It bridges the gap between concrete existence and theoretical absence, indicating that the cosmos is a vibrant, dynamic place where reality is far more intricate than it first appears. The world underneath our feet and the stars above our heads is anything but empty. It is filled with a breathtaking array of possibilities just waiting to be explored. When physicists talk about empty space or a void, they are referring to regions of the universe that appear to lack matter and energy. This might conjure up an image of nothingness, a vast ocean devoid of any substance. However, the reality is much more fascinating. Even in these seemingly empty areas, physical phenomena are occurring. At the most fundamental level, the vacuum of space is not truly empty. It is filled with quantum fluctuations, which are brief and spontaneous changes that occur at the subatomic level. This means that even in a vacuum, particles can appear and disappear in a very short span of time. This phenomenon implies that empty space can still exhibit characteristics that challenge our traditional understanding of what nothing means. Moreover, the concept of a void also relates to the structure of the universe. Large-scale voids, where galaxies are sparse, provide insight into the universe's evolution. These empty regions have been shaped by gravitational interactions over billions of years, leading to the clustering of matter and the cosmic web structure we observe today. This intricate tapestry suggests that even what we think of as simply unoccupied is crucial to the formation of galaxies and the universe as we know it. Additionally, the vacuum is also a stage for the interactions of dark energy, which is driving the accelerated expansion of the universe. So, while we might picture empty space as devoid of life and activity, we are continually discovering that it is a dynamic, lively arena. The void is not merely nothingness, but teems with potential and plays a pivotal role in the grand narrative of the cosmos. Black holes are fascinating cosmic phenomena that sit at the edge of our understanding of space, time, and the concept of nothingness. When we consider a black hole, we envision a region in space where gravity is so strong that nothing, not even light, can escape its grasp. This creates an intriguing paradox. By peering into the properties and behaviors of black holes, we gain insight into the very nature of existence and the void surrounding it. One of the most profound contributions of black holes is their relationship with gravity and the fabric of spacetime. According to Einstein's theory of general relativity, black holes warp spacetime around them significantly. This bending of spacetime leads to the idea that when something crosses the event horizon, it is as if it is disappearing into a kind of nothing. This intersection of solid physical laws and an apparent absence provides a framework for exploring fundamental questions about reality. Additionally, black holes offer a unique perspective on entropy and information. They raise significant questions about what happens to information when it falls into a black hole. The debate surrounding this poses profound implications for our understanding of the universe. If information is lost in black holes, it challenges the fundamental laws of physics, particularly the principle of conservation of information, which suggests that information cannot be created or destroyed. Thus, exploring these enigmatic entities may reveal more about the nature of nothingness itself. Finally, black holes also challenge our perceptions of creation and destruction. They serve as a reminder that from the annihilation at their centers, new stars and galaxies can be born in the aftermath of their formation. This cosmic recycling hints at a deeper understanding of existence itself, implying that nothing is ever truly erased. Instead, black holes play a vital role in the ongoing narrative of the universe's life cycle, intricately blending the themes of creation and cosmic void, thus enhancing our understanding of what nothing really means in the grand scheme of things. The concept of nothing is intriguingly pivotal within the framework of thermodynamics, particularly when we think about the nature of systems and energy. In physics, nothing is often associated with a vacuum, a state devoid of matter and energy. However, when we delve deeper, we uncover that even what we consider to be nothing can hold significant implications for thermodynamic laws, especially the first and second laws. The first law of thermodynamics, which states that energy cannot be created or destroyed, implies that the total energy of an isolated system remains constant. But what happens when we talk about a state of nothingness? It introduces a fascinating scenario where fluctuations in energy might appear. Even in a vacuum, there can be spontaneous energy fluctuations, which are the basis for virtual particles spontaneously appearing and disappearing. This highlights that nothing isn't quite empty. Rather, it is a complex state teeming with unseen potential. Then we have the second law of thermodynamics, which revolves around entropy, or the measure of disorder within a system. Interestingly, even in a vacuum, as you approach absolute zero, entropy reaches its minimum. However, the notion of nothing becomes more complex here because true nothing would theoretically have zero entropy. But in practical terms, scientists find that true absolute zero is unattainable, suggesting that even in our search for nothing, entropy plays its part. This interplay of nothing within thermodynamics opens doors to intriguing discussions about the universe's origins and fate. It challenges our understanding of existence and invites us to ponder whether true nothingness is even achievable. Thus, the relationship between nothing and thermodynamic laws is remarkably profound, bridging physical concepts with philosophical inquiries about reality itself. The origin of the universe is one of the most captivating questions in cosmology. For centuries, thinkers and scientists have pondered how our vast universe could come into existence from nothing. One of the prevailing theories is the concept of the Big Bang, which suggests that about 13.8 billion years ago, all matter and energy were concentrated in an infinitely small point. This point then expanded explosively, leading to the formation of space, time, and the building blocks of matter that would later come together to form stars, galaxies, and everything we observe today. Interestingly, the Big Bang theory suggests that the notion of nothing is not as straightforward as it seems. When we talk about the universe emerging from nothing, it's important to note that this nothing could possibly include quantum fluctuations. Quantum physics tells us that particles pop in and out of existence constantly, so what we perceive as a void might actually be a seething background of energy. This idea proposes that the universe could have emerged from these quantum fluctuations in a seemingly empty state, blurring the line between nothing and something. Another fascinating perspective comes from the theory of cosmic inflation. This concept posits that after the Big Bang, a period of rapid expansion occurred, exponentially stretching the fabric of the universe. During this incredibly brief moment, the universe grew from subatomic scales to sizes larger than galaxies almost instantaneously. This inflationary phase could also explain the uniformities we see in the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. Finally, some scientists explore the idea of a multiverse, a collection of countless universes existing parallel to our own. This theory proposes that our universe may be just one of many, each with different properties and laws of physics. In this view, the birth of our universe from nothing might simply be one event among many, providing a deeper layer of intrigue to the question of origins. The quest to understand how the universe began continues to inspire and challenge scientists, leading us to question not only the cosmos, but also the very nature of existence itself. The Big Bang theory suggests that about 14 billion years ago, our universe began as an incredibly dense and hot point known as a singularity. This singularity contained all the energy and matter that would eventually become our universe, tightly compressed into a minuscule space. The laws of physics as we understand them break down under these extreme conditions, making it difficult to comprehend what this singularity truly was or how it existed. Then, in a monumental event, this singularity began to expand. This expansion is what we refer to as the Big Bang, an explosion of energy and matter that sent everything flying outward. As the universe expanded, it also cooled. In the first moments following this explosion, fundamental particles such as protons, neutrons, and electrons began to form. This process marked the universe's transition from pure energy to matter, laying the groundwork for everything that would come later. As this cooled and expanding universe continued to evolve, these particles began to group together, forming simple elements like hydrogen and helium. Over millions of years, these elements clumped under the force of gravity, eventually leading to the formation of stars and galaxies. So, from a singularity, an array of galaxies emerged, each containing countless stars, some with their own planetary systems. What is truly fascinating is that even today, we can observe traces of this early expansion. The cosmic microwave background radiation is a remnant of the heat from the Big Bang, detected as a faint glow that fills the universe. This observable evidence supports the idea that everything we see around us originated from this extraordinary beginning, reminding us that we are all made from the remnants of that first explosive moment. The concept that the universe originated from nothing may seem counterintuitive, but it is supported by several intriguing pieces of scientific evidence. One of the primary notions comes from the Big Bang theory, which describes the universe as starting from an extremely hot and dense state. This theory suggests that approximately 13.8 billion years ago, all the energy and matter we see today was concentrated in a tiny point before rapidly expanding. This expansion marked the birth of our universe. In recent years, advancements in observational astronomy have provided compelling support for this model. For instance, scientists have observed the cosmic microwave background radiation. This faint glow filling the universe is considered a remnant from the early moments after the Big Bang. Essentially, it acts as a snapshot of the universe when it was just about 300,000 years old, confirming the existence of a hot, dense origin point. Moreover, quantum physics introduces the fascinating idea that particles can spontaneously appear and disappear in a vacuum. This phenomenon suggests that nothing is not just empty space, but rather a froth of potentiality. Some physicists propose that the entire universe might have emerged from such quantum fluctuations, allowing the universe to come into existence from what we perceive as nothing. This challenges our everyday understanding of creation and existence. Finally, when we consider the concept of causality, the idea that everything must have a cause, the emergence of the universe from nothing presents a compelling question for scientists and philosophers alike. It invites us to rethink our assumptions about time, existence, and the very nature of the universe. As we explore these themes, it becomes clear that the possibility of a universe arising from nothing is supported by both empirical evidence and revolutionary theories in modern physics. Our understanding of cosmic inflation has significantly reshaped the way scientists view the origin of the universe. Before the theory of inflation came about, the leading idea was the Big Bang, which suggested that the universe started as an extremely hot and dense point. It expanded rapidly, but it did not fully explain some puzzling observations, such as why the universe appears so uniform on large scales despite its immense size. This led to questions about what happened right at the very beginning of it all. Cosmic inflation, proposed in the early 1980s by physicist Alan Guth and others, introduced the idea that the universe underwent an exponential expansion during its first moments, just a fraction of a second after the Big Bang. During this brief period, the universe inflated vastly larger than the entirety we see today. This rapid expansion helped to smooth out any irregularities, leading to the homogeneous and isotropic universe we observe. Essentially, it resolved the issues of uniformity and structure, providing a compelling framework for understanding our cosmos. Additionally, inflation theory suggests that tiny fluctuations in density, born from quantum mechanics, laid the groundwork for the formation of galaxies and large-scale structures. These variations in density were stretched to cosmic scales during inflation. When galaxies formed, they grew from the parts of the universe that had slightly more mass than others. This mechanism helps explain the cosmic microwave background radiation, which is a remnant of the early universe, illustrating the tiny variations we see today. With this framework, many scientists have come to view the universe's origin not just as a singular event, but as a complex process influenced by higher dimensional spaces and fields. Cosmic inflation has also opened new avenues in our search for answers, connecting ideas from particle physics to cosmology. As researchers continue to collect and analyze data from the cosmos, the echoes of inflation promise to reveal even more about how our universe came into being. This fascinating journey highlights how our exploration of the universe's beginnings is as dynamic as the cosmos itself. The study of cosmic microwave background radiation, or CMB, is a fascinating window into the early universe. This faint glow of radiation permeates the universe and is a remnant from the time when the cosmos was just a hot, dense soup of particles. Roughly 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into hydrogen atoms, allowing light to travel freely. This released the CMB, which carries with it a wealth of information about the universe's infancy. By analyzing the CMB, scientists can glean critical insights into the conditions of the early universe. The slight fluctuations in temperature and density within this radiation map correspond to the seeds of galaxies and large-scale structures we see today. These variations are essential for understanding how matter clumped together over millions of years to form stars and galaxies. Furthermore, these patterns provide evidence supporting the Big Bang theory, marking the universe's rapid expansion during a period known as inflation. Moreover, the CMB allows scientists to determine the overall composition of the universe. By measuring the radiation's properties, researchers can estimate the proportions of normal matter, dark energy present. This knowledge is pivotal. It defines not only the present state of the universe, but also its fate. For instance, our understanding of dark energy's influence helps scientists predict whether the universe will continue to expand indefinitely or eventually collapse in on itself. Ultimately, the study of cosmic microwave background radiation paints a detailed picture of the universe's early moments, illuminating the processes that led to the cosmos we inhabit today. This research not only deepens our understanding of cosmology, but also fuels ongoing curiosity about the fundamental forces that shape our existence in the vast universe. The concept of the multiverse offers a fascinating perspective on the origins of everything, presenting a view that transcends our traditional understanding of the universe. It posits that our universe is just one of many, possibly an infinite number, existing in a vast cosmic landscape. This idea pushes the boundaries of cosmology and challenges the notion that all reality can be explained by a single universe beginning with the Big Bang. In the framework of the multiverse, the origins of everything might not emerge from a singular event, but rather from a process where different universes are born with their own unique sets of physical laws. Some theories suggest that these multiple universes could arise from quantum fluctuations in a primordial state, where different regions of space-time expand and evolve independently. This suggests that what seems to be nothing in one context can give rise to various somethings, each displaying distinct characteristics. One of the most intriguing implications of the multiverse theory is that it can provide a solution to some of the major questions in cosmology. For instance, it addresses the fine-tuning problem, which questions why certain physical constants appear to be perfectly calibrated to allow life. In a multiverse, it's not surprising that at least one of those universes would have the right conditions for life, while countless others might not. Ultimately, while the idea of a multiverse remains speculative, it invites us to reevaluate our understanding of the universe's origins and the fabric of reality. Rather than a unique beginning, the multiverse suggests an everlasting tapestry of cosmos, where the birth of one universe might simply be a local occurrence amidst a vast array of potential realities. This grand vision of cosmic plurality ignites a sense of wonder about our place in the universe and the mysteries that lie beyond. The Planck Epoch is the very first moment of our universe, occurring just a fraction of a second after the Big Bang, specifically within the first 10 to the minus 43 seconds. This era is significant because it represents a state of existence where the laws of physics, as we understand them today, break down. During this incredibly brief period, the universe was extremely hot and dense, and all four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified as one. What truly fascinates scientists is how this epoch relates to the concept of creation from nothing. The conventional view of creation assumes that something must come from something else. However, in the context of the Planck Epoch, the universe might have emerged from a quantum fluctuation, illustrating how the very fabric of space-time could allow for the existence of reality where previously there was none. This idea challenges our intuitions about the origins of the cosmos, suggesting the potential for something to arise from nothing in the form of energy transforming into matter. The significance of the Planck Epoch extends beyond mere origins. It poses profound philosophical questions about existence, causality, and the nature of reality itself. Some researchers suggest that understanding this era can help us grasp how the universe may have evolved and what the boundaries of our physical theories are. It represents a frontier where both science and philosophy intertwine, leading to new interpretations of how we view our place in the cosmos. Ultimately, investigating the Planck Epoch not only sheds light on the early moments of the universe, but also inspires awe regarding the very nature of existence. A time when the universe itself is believed to have sprung from an unfathomable state invites us to consider the fundamental principles of creation and evolution, pushing the limits of our imagination and understanding. In our quest to understand the universe's origins, two mysterious components play pivotal roles: dark matter and dark energy. Both of these entities are elusive, yet they significantly influence the structure and expansion of our cosmos. Dark matter, which makes up about 27% of the universe, does not emit, absorb, or reflect light, making it invisible to traditional instruments. Its presence is inferred from the gravitational effects it has on visible matter, radiation, and the large-scale structure of the universe. Essentially, dark matter acts like a cosmic glue, helping to hold galaxies together and shaping the universe we see today. On the other hand, dark energy accounts for roughly 73% of the universe and is believed to be responsible for its accelerating expansion. While the exact nature of dark energy remains a mystery, it appears to work against gravity, pushing galaxies apart. This acceleration suggests that the universe is not just expanding, but its expansion is speeding up, an unexpected twist to our understanding of cosmic evolution. The interplay between dark matter and dark energy is crucial for models of the universe's early moments, particularly during an event called cosmic inflation. Understanding these components also helps scientists piece together the timeline of the universe. In the wake of the Big Bang, the universe was a hot, dense state that rapidly expanded. As it cooled, matter began to form. The balance between dark matter and dark energy became especially relevant as the universe evolved, influencing how quickly structure formed and how galaxies clustered together. By studying these phenomena, researchers can trace back the conditions that gave rise to our current cosmic landscape. The ongoing exploration into dark matter and dark energy not only deepens our comprehension of the universe's beginnings, but also raises new questions about its ultimate fate. As we gather more evidence from astronomical observations and theoretical physics, we edge closer to unveiling the secrets of these cosmic enigmas and understanding the very nature of space and time itself. Advancements in technology have dramatically reshaped our understanding of the universe's origins. When we peered into the heavens using early telescopes, we could only glimpse the stars and planets. However, as technology progressed, so too did our ability to observe the cosmos. The advent of space-based telescopes like the Hubble Space Telescope has provided us with breathtaking images and data that illuminate the far reaches of space, allowing us to see galaxies billions of light-years away and observe phenomena that were previously beyond our grasp. One of the most significant impacts of technology is the development of instruments that can detect waves in space. Gravitational wave detectors such as LIGO have opened an entirely new field of astrophysics. By capturing the ripples caused by massive celestial events like colliding black holes, we have gained vital insights into how these events unfold. This has not only confirmed predictions made by theories like Einstein's general relativity, but has also provided clues about the birth and evolution of the universe itself. Moreover, advancements in particle physics have further enriched our understanding of the beginnings of everything. High-energy particle accelerators, such as the Large Hadron Collider in Switzerland, enable scientists to recreate conditions that existed just moments after the Big Bang. By smashing particles together at incredible speeds, researchers can uncover the fundamental building blocks of matter and explore the forces that shaped the early universe. These experiments provide evidence for theories like the Higgs boson, which plays a critical role in our understanding of mass and energy. As we continue to innovate and develop new technology, our theories about the origins of everything will undoubtedly evolve. Each new discovery builds upon the last, drawing a more intricate picture of the universe's history. With every advancement, we move closer to answering profound questions about our existence, questions that have captivated humanity for centuries. In this grand quest for knowledge, technological progress serves as both our lens and our key, unlocking further mysteries of the cosmos. The concept of creating something from nothing is a profound topic that often intersects with the nature of time itself. When we delve into this discussion, we encounter the question of whether time is a fundamental aspect of the universe or merely a construct of human perception. Traditionally, we think of time as a linear progression where the past leads to the present, which in turn shapes the future. However, in the context of cosmology, time's role can take on a more complex dimension. In many cosmological models, particularly those associated with the Big Bang theory, time itself came into existence along with space. This means that before the Big Bang, when there was purportedly nothing at all, time, as we understand it, did not exist. This raises an intriguing philosophical question. Can we speak of before the universe was created if there was no time for such a concept to exist? It challenges our intuitive grasp of causality, where cause and effect rely on time's flow. Once we step into the universe's unfolding, time becomes a critical player in understanding the processes that lead to the creation of matter and energy. Quantum mechanics introduces an element of uncertainty and probabilistic behavior at the subatomic level, suggesting that particles can appear spontaneously under certain conditions. This phenomenon prompts scientists to explore whether particles can emerge from a vacuum in the absence of time, leading us to reconsider the very definition of nothing and how it might relate to the beginnings of our universe. Ultimately, the discussion of creating everything from nothing cannot be decoupled from time. It requires us to rethink the very nature of existence, an adventure that weaves together science, philosophy, and our deepest curiosities about the cosmos. As we continue probing these profound questions, we find that time is not merely a backdrop, but an integral part of the narrative that shapes our universe and our understanding of existence itself. When we explore the concept of nothing, we find ourselves at an intriguing crossroads of science and philosophy. In scientific discourse, particularly in cosmology, nothing often refers to a vacuum, a space devoid of matter. However, this void is not truly empty. Even in seemingly empty space, there are fluctuations of energy and virtual particles popping in and out of existence. This understanding comes from quantum physics, where the characteristics of nothingness are dynamic and teeming with activity, countering our intuitive perception of emptiness. On the philosophical side, the exploration of nothing transcends mere physical definitions. Philosophers consider nothingness a profound concept that touches on existence itself. They question what it means to say something exists and the implications of a realm where nothing does. For them, nothingness poses a paradox. How can one discuss or think about nothing if nothing is the absence of everything, including thought itself? Philosophers like Martin Heidegger have tackled these ideas, emphasizing that understanding nothing is pivotal to grasping being, existence, and the very nature of reality. These contrasting approaches create a rich dialogue between science and philosophy. While scientists might focus on the measurable implications of empty space, philosophers delve into the existential significance and implications of nothing. This interplay encourages deeper inquiry from both fields, prompting questions like, what was there before the universe began? Is true nothingness even attainable? Ultimately, the theories scientists propose must coexist with the philosophical musings they inspire, illustrating the profound complexity of the universe. As we seek answers, the journey itself can be as enlightening as the conclusions we reach, revealing layers of meaning behind the simplest of concepts. Each discipline enriches our understanding of nothing, allowing us to appreciate the intricate tapestry that is our existence. Throughout history, the concept of void or nothingness has been intricately woven into various cultural narratives about creation. Many traditions across the globe illustrate the void not merely as emptiness, but as a fertile ground for potential and transformation. For instance, in many ancient mythologies, the cosmos begins with a formless void, a primordial state that holds the promise of life. This idea resonates with listeners, as it speaks to the universal theme that from nothing, everything can arise. In Hindu mythology, for example, the cosmic void is often associated with Lord Vishnu, who rests on the infinite ocean of nothingness, representing both emptiness and the ultimate source of creation. From this stillness, the universe is birthed through a cosmic dance, illustrating the intertwining relationship between absence and existence. This narrative emphasizes that the void is not static but dynamic, brimming with the energy of possibility. Similarly, in ancient Greek philosophy, the concept of chaos represents a state of disordered nothingness that precedes creation. This chaos, far from being merely chaotic, encapsulates the potential for order and form. It is a space where the first elements emerge, illustrating the idea that from disorder can spring forth harmony. The Greeks, like many cultures, recognized that the void is not simply a lack, but a foundational perspective on how reality manifests. Across different cultures, the void symbolizes both the beginning and the end, a paradox that captivates the human imagination. Whether through myths, philosophies, or spiritual outlooks, the narratives reveal a profound acknowledgement of the void as an integral part of the creation process, embodying both fear and wonder. As we examine these stories, we find a deeper understanding of our existence, reminding us that creation often arises from the quiet depths of potential. The concept of creation from nothing is a profound theme that emerges in the myths and legends of various cultures around the world. In many traditions, this idea is closely linked to the emergence of the universe and the birth of existence itself. For instance, in ancient Mesopotamian mythology, the chaotic waters were thought to exist before anything else. From this primordial chaos, the god Marduk arose to create the world, separating the waters and forming the heavens and the earth. This narrative highlights the idea that creation is born from both nothingness and a deeper inherent existence, illustrating the transition from potential to reality. Such themes resonate deeply, suggesting that the creative process often encompasses cycles of rest, awakening, and manifestation. In contrast, in the Judeo-Christian tradition as described in the Book of Genesis, God creates the world by speaking it into existence. "Let there be light," he declares, and suddenly light separates from darkness. This simple yet powerful act of divine will emphasizes the notion of creation as an intentional act, originating from an omnipotent being. This narrative has significantly influenced Western thought about existence and the divine, establishing a foundation where creation is fundamentally linked to a singular source. These diverse representations from various cultures all convey a similar wonder at the mystery of existence. They invite us to ponder the origins of the universe and our place within it. As we explore these myths, we see a tapestry woven with the threads of imagination, spirituality, and humanity's desire to understand the often unexplainable phenomenon of creation from nothing. Each story adds depth, offering insights into how different peoples have grappled with the fundamental questions of life and existence. The idea that everything originates from nothing poses profound ethical implications that reach into the very fabric of our beliefs and understanding of purpose. When we consider the universe and existence itself arising from a state of nothingness, it challenges traditional views about the nature of creation, existence, and ultimately, our responsibilities as conscious beings. If everything we know comes from this void, one must ponder what value or significance our actions hold in a universe that began with no intention or inherent meaning. This perspective evokes significant questions about our role in the universe. If life and the cosmos are merely products of chance, does that diminish our moral responsibilities, or does it elevate them? Recognizing that every action, thought, and creation stems from the same primordial nothing might inspire a sense of unity, urging us to treat our environment and fellow beings with greater care and empathy, understanding that we are all part of this intricate, interconnected tapestry of existence. Moreover, this notion can influence our view of progress and development. If all arose from nothing, it suggests a potential for transformation and regeneration that should not be underestimated. Each individual has the ability to contribute to the evolution of ideas, community, and culture. Viewed in this light, the ethical implications also suggest a commitment to stewardship. Knowing that our actions can either enhance or detract from this grand unfolding encourages a more conscientious approach to how we interact with the planet and each other. Grappling with the implications of everything resulting from nothing invites us to reconsider the underlying philosophies that guide our lives. Instead of seeing ourselves as solitary beings adrift in a purposeless void, we can embrace the idea that we have the capacity to create meaning and impact, fostering a sense of ethical responsibility that resonates deeply with our shared human experience. The realization that our existence is a remarkable phenomenon may inspire us to approach life with wonder, care, and dedication to the well-being of all. The theory of nothingness presents us with a profound philosophical inquiry that challenges our understanding of existence itself. At its core, this theory plunges into the question of what it means for something to exist. In a universe where everything seems to be made up of something, contemplating nothingness forces us to consider what lies beyond matter, energy, and even space and time. It raises the unsettling thought: if nothingness precedes existence, what does that imply about our lives and the very nature of reality itself? Embracing this perspective, we begin to see how foundational nothingness is to the cosmos. Before the Big Bang, it is theorized there was nothing, no time, no space, and no matter. This concept invites us to consider that existence is not a given but a remarkable occurrence in an otherwise empty void. This realization can inspire awe. Life, with all its complexities and emotions, arises from an initial state of nothingness. It makes our experiences feel even more precious as they emerge from a universe that was once devoid of everything we know today. Moreover, reflecting on nothingness invites us to rethink our values and priorities. If existence is a rare and fragile phenomenon, should we not strive to appreciate the moments we have? This perspective can lead to a deeper appreciation of life's transient nature. Recognizing the significance of existence against the backdrop of nothingness can encourage mindfulness and gratitude, nudging us to live more fully in the present. Lastly, the exploration of nothingness also speaks to our existential struggles. It confronts us with questions of purpose and meaning. If the universe began from nothing, then our search for meaning may be rooted in a fundamental human desire to create significance in an indifferent cosmos. Thus, contemplating nothingness not only alters our view of existence, but also empowers us to shape our understanding of life and our place within the grand tapestry of the universe. Language and communication are essential tools that shape how we perceive and understand concepts in the universe, including the seemingly abstract idea of nothingness. When we discuss nothing, we often find ourselves caught in a paradox. It is difficult to talk about nothing because using words implies that we are filling a void with meaning. This duality can lead us to consider whether nothing truly exists or if it's simply a construct of our language. In many cultures, the concept of nothingness can vary significantly. For instance, some languages have specific terms for emptiness, while others might struggle to encapsulate the idea at all. This diversity reflects different worldviews and philosophies. For example, in Eastern philosophies, the notion of emptiness or void plays a central role, suggesting that nothingness can be a state of potential and possibility rather than mere absence. Meanwhile, in Western thought, nothing has often been viewed through a more nihilistic lens, focusing on the absence or lack of being. Furthermore, the ways we communicate about nothing can influence our emotions and cognitive processes. Phrases like feeling empty can evoke strong feelings of despair or loss. Conversely, discussing nothing in scientific terms, such as in quantum physics, which considers vacuum states or the void of space, introduces intriguing ideas. Here, nothing isn't merely emptiness, but a dynamic state full of potential for energy and matter to emerge. Ultimately, our linguistic frameworks guide our understanding and emotional responses to nothingness. Through dialogue, literature, and science, we delve deeper into these concepts, continuously piecing together how nothingness impacts our existence and the universe. In a way, while we might strive to understand nothing, our very attempts to articulate it keep filling that void with meaning and exploration. The concept of nothing is far more complex than it may seem. Often we think of nothing as simply an absence or void. However, in philosophy and cosmology, nothing takes on deeper significance. For instance, in quantum physics, the vacuum of space is not truly empty. It is filled with fluctuations and virtual particles that seem to pop in and out of existence. This notion challenges our traditional understanding of reality, suggesting that what we perceive as nothing can have real effects on the universe. In terms of perception, acknowledging nothing can fundamentally alter how we see existence. If we consider emptiness as an essential component of everything around us, it leads to profound implications. It invites us to question the nature of reality itself. Is the universe an assemblage of tangible objects, or does it thrive within a context of voids and absences that give structure and meaning to our existence? This interplay between something and nothing shapes not just cosmic phenomena, but also our thoughts and philosophical inquiries into why we are here. Furthermore, the contemplation of nothingness is a significant theme in various cultures and philosophies. The idea can evoke feelings of emptiness, but also elicit a sense of freedom. By embracing nothing, we might find clarity, an understanding that life's complexities often stem from hidden depths of stillness and potential. Many spiritual traditions explore this notion, suggesting that recognizing nothingness can lead to a more profound appreciation of being. Ultimately, the concept of nothing not only influences our scientific understanding, but also enriches our existential reflections. It acts as a backdrop against which all of reality plays out. By examining this interplay, we can foster a richer dialogue about existence, one that embraces both the tangible and the intangible, encouraging us to explore not only what is present, but also what is not. Understanding nothing, often referred to as the concept of emptiness or void, plays a surprisingly pivotal role in the study of consciousness. To many, nothing might seem like a lack of substance, but in the realm of philosophy and neuroscience, it opens up profound discussions about awareness and perception. This exploration can lead us to consider what consciousness is when it is stripped of experiences, thoughts, and emotions, essentially when we try to grasp the essence of being conscious without any content. When we contemplate nothingness, we engage in deep introspection about what it means to be aware. This can bring forth the realization that consciousness is not merely a collection of experiences, but a fundamental aspect of our being. In moments of meditation and profound silence, individuals often report heightened awareness of their thought processes, revealing how consciousness can exist in a state devoid of stimulation. This suggests that understanding emptiness aids in distinguishing between consciousness itself and the myriad contents that fill our minds. Research in neuroscience has begun to back up these contemplative insights. Studies show that during states of deep meditation, brain activity often shifts into patterns associated with resting states, where one might experience a sense of nothingness. This state allows individuals to explore their own consciousness more deeply, leading to insights about the nature of thought and awareness. It suggests that by understanding nothing, we may unravel the complexities of consciousness, moving towards grasping its true character. Grappling with the concept of nothingness can ultimately lead us not only to a deeper understanding of consciousness, but also to greater self-awareness. It encourages a valuable journey inward, prompting us to examine the layers of our experiences while recognizing that the essence of being aware transcends the clutter of daily life. Embracing this void may reveal more about who we are and how we relate to the cosmos at large. The discussion of nothingness invites us to ponder profound philosophical questions about existence and our place in the universe. When we explore the concept of nothing, we are not just considering the absence of matter or energy, we are also engaging with the very nature of reality and consciousness. This exploration can evoke feelings of existential wonder, prompting us to reflect on what it means to be alive and how we derive meaning in our lives. For many, contemplating nothingness can provoke feelings of anxiety or despair. The vastness of the universe and the ultimate fate of existence might lead one to feel insignificant. However, this discourse also opens up pathways to understanding that purpose can be derived from our personal experiences, relationships, and contributions to the world around us. Instead of viewing a vast, indifferent universe as a source of dread, we can see it as an invitation to carve out our own path and cultivate significance through human connections and achievements. This discussion also challenges the conventional boundaries of science and philosophy, encouraging a rich dialogue that explores the intersection of knowledge and belief. The more we seek to understand our origins and the fabric of reality, the more we may find a sense of unity and connection with each other and the cosmos. Such contemplative journeys can transform our perception of nothingness from an abyss of uncertainty to a canvas where we can paint our narratives of purpose. Ultimately, our engagement with the idea of nothingness serves as a catalyst for personal evolution. It can inspire us to seek out new experiences, deepen our understanding of one another, and assert our unique purpose in the broader tapestry of life. As we embrace the complexities of existence, the challenge of finding meaning amid nothing becomes not just an intellectual exercise, but a deeply personal quest that enriches our lives. The concept of nothingness has inspired a diverse range of artistic expressions across various cultures, reflecting unique philosophical and aesthetic perspectives. In many Eastern traditions, especially within Zen Buddhism, nothingness is often celebrated through minimalist art forms. This can be seen in inkwash painting, where the absence of detail creates a sense of openness and tranquility. The emptiness on the canvas invites contemplation, encouraging viewers to find meaning in the space that is left unfilled. In Western art, the approach to nothingness can be quite different. Artists like Yves Klein and Kazimir Malevich explored the idea of the void, but often did so in an assertive manner. Klein's famous blue monochrome invites the viewer to engage with a single color which, while seemingly void of variety, evokes profound emotional responses. Similarly, Malevich's work in the suprematist movement proposed that reduction to geometric forms could lead to a deeper understanding of existence, stripping away the non-essential. Native American art also provides an intriguing take on nothingness, often conveying themes of emptiness in connection to nature. For many indigenous artists, the representation of space and the relationship between figures and their environment explores the balance of presence and absence. These expressions do not aim for a literal interpretation of nothingness, but invite reflections on life's interconnectedness, allowing viewers to experience emptiness not as a lack, but as a source of potential and infinity. Ultimately, artistic expressions of nothingness transcend mere aesthetics. They reflect profound cultural philosophies. Whether emphasizing meditation, emotion, or a connection to the universe, each tradition offers a unique lens through which we can explore this elusive concept. Through these varied expressions, nothingness becomes a rich tapestry of meaning, encouraging us to ponder not just what is absent, but what that absence reveals about our own existence. Theories of regeneration offer a fascinating lens through which we can explore the transition from nothing to everything, especially when we consider the origins of life and the universe. Regeneration involves the idea that life can return from a state of being dormant or seemingly absent to a vibrant and complex existence. This mirrors the way the universe itself evolved from a state of nothingness, expanding into the rich diversity of galaxies, stars, and planets we see around us today. At the heart of regeneration lies the potential for renewal and growth. In biological terms, certain species can regenerate lost limbs or even entire organs, suggesting that life possesses an intrinsic ability to restore itself. This process can be likened to the early moments of the universe. When the Big Bang occurred, what might have appeared as a void exploded into a tapestry of matter and energy. Just as organisms harness their genetic information to rebuild and recover, the universe utilized fundamental forces and particles to assemble the myriad structures we now study. Moreover, regeneration theories highlight resilience and adaptation, qualities inherent in both life forms and cosmic evolution. For instance, in environments where life faces extreme challenges, some species exhibit remarkable adaptation mechanisms. This adaptability is reflected in the universe's evolution as it shifted and adapted after its inception. Galaxies collided, stars formed, and black holes developed. Every event contributed to the grand tapestry of cosmic history as matter coalesced into complex structures. Ultimately, the journey from nothing to everything is encapsulated beautifully in regeneration. It speaks to the possibility of transformation and growth, whether within individual organisms or across the cosmic expanse. Theories of regeneration remind us that life, in all its forms, and the universe itself are interconnected processes, continually evolving and revealing the potential for renewal at every scale. Natural cycles are a profound reminder of the concept that everything can emerge from nothing. In nature, we see this phenomenon play out in various processes that illustrate how matter and energy transform and regenerate, seemingly from absence into existence. Consider the changing of the seasons as an example. Each year begins with the retreat of winter, a time when many organisms appear dormant, yet from that barrenness, spring bursts forth with vibrant life. This cycle emphasizes how even during periods of seeming emptiness, potential is always present, waiting to be awakened. Another striking example is found in the water cycle. Water evaporates, turning from liquid to vapor and disappearing from sight, an action that might lead one to think it has simply vanished. But later, it condenses in the atmosphere to form clouds and eventually falls back to the earth as precipitation. In this continuous loop, water transitions between states, illustrating that apparent absence is just a part of a larger system of transformation. It underscores the idea that nothing truly goes away. It merely reconfigures into something new. In the world of ecosystems, we see similar cycles where decay and renewal are closely linked. When a tree falls, it may seem like a loss, but that tree provides nutrients to the soil, supporting new growth. From this decay emerges a multitude of life forms, returning to the earth what was once taken. This cycle embodies the philosophical idea that absence can give rise to presence, reminding us that in nature, endings often herald new beginnings. Ultimately, natural cycles illustrate a fundamental truth about existence, that from what appears to be nothing, life and matter continually re-emerge. Through these observations, we can appreciate a beautiful interconnectedness, revealing how the fabric of nature weaves together the presence and absence of all things. In every cycle, there's a poignant reminder of this profound principle, a grand dance of life, always in motion, always renewing itself. The journey of star formation is a captivating tale of creation out of the vast emptiness of space. It starts in regions known as molecular clouds, which are made up of gas and dust. These clouds are often referred to as stellar nurseries because they provide the essential ingredients for new stars to emerge. The process begins when a disturbance, perhaps from a nearby supernova or the collision of two clouds, causes a part of the molecular cloud to collapse under its own gravity. As the gas and dust collect, they begin to heat up and form a dense core. This core continues to accumulate material, growing hotter and denser. When the temperature and pressure within the core reach the point where nuclear fusion can occur, a star is born. This moment marks the transformation of mere gas and dust into a shining celestial body, illuminating the darkness of space. What was once an area of nothingness now radiates light and warmth, showcasing the beauty of creation from the cosmos. Interestingly, this process does not end with the birth of a star. Once a star has formed, it enters a long life of fusion, converting hydrogen into helium and even heavier elements as it ages. Throughout this life cycle, stars play a crucial role in enriching their surroundings. When they eventually end their lives, either as supernovae or gentle fades, they scatter materials back into the cosmos, providing the building blocks for new stars, planets, and even life. This cyclical nature of creation reflects a profound and ongoing narrative where each death contributes to the life of the next generation. The story of star formation beautifully encapsulates the theme of creating from nothing. It illustrates how vast, empty space can become vibrant and full of life through the innate processes of the universe. Each star that lights up the night sky is not just a glowing point of light. It is a testament to the incredible transformation that occurs when gas and dust come together, demonstrating the complexities and wonders of cosmic creation. Supernovae are among the most spectacular events in the universe, serving as both cosmic fireworks and crucial factories for the creation of new elements. When a massive star reaches the end of its life, it exhausts its nuclear fuel, creating a situation of imbalance. The core collapses under gravity, leading to an explosive outburst that can outshine entire galaxies for a brief period. This explosion is not merely destruction. It is a transformative process that generates and disperses a wealth of elements across the cosmos. During the supernova event, temperatures soar to staggering levels. In this fiery crucible, pre-existing atomic nuclei can collide and fuse together, forming heavier elements. For instance, hydrogen and helium, which are the simplest and most abundant elements, can combine under these extreme conditions to create elements like carbon, oxygen, and even iron. Each supernova explosion contributes to the supply of these heavier elements, enriching the interstellar medium, the vast stretches of space filled with gas and dust between the stars. After the explosion, the remnants of a supernova, known as supernova remnants, scatter these newly created elements throughout the galaxy. This dispersal is crucial for the cosmic cycle of matter. The elements from supernovae mix with existing clouds of gas, providing the building blocks for future stars, planets, and eventually life. Without these cosmic explosions, our universe would lack many of the essential elements that make up everything we see around us. Supernovae play a vital role in the generation of new elements, transforming cosmic emptiness into a rich tapestry of materials. This process not only fuels the formation of new celestial bodies, but also continues the cycle of creation in our universe, weaving a connection between the death of one star and the birth of many others. Ecological models provide a fascinating lens through which we can explore how life emerged from lifelessness on our planet. These models simulate biological systems, showing how various factors interact over time to create complexity and diversity. Imagine an empty canvas, representing a lifeless world, gradually painted by the brushstrokes of natural processes, leading to a vibrant ecosystem. At the heart of these models is the concept of self-organization. This principle suggests that, given the right conditions, simple life forms can emerge and evolve into more complex organisms. For instance, Ecological models often explore how temperature, light, and chemical availability influence the formation of organic compounds. These compounds then undergo various interactions, eventually fostering primitive life forms that can adapt and thrive in changing environments. Moreover, the models illustrate how cooperation and competition drive evolution. Early life forms, like bacteria, might share resources in a cooperative manner, fostering growth that leads to diversity. At the same time, competition for those same resources creates a dynamic struggle where only the most adapted organisms survive. Over eons, this delicate balance of cooperation and competition shapes the elaborate tapestry of life we see today. Ultimately, ecological models serve as a bridge connecting the realms of chemistry, biology, and evolution, allowing us to understand how lifeless atoms and molecules could evolve into complex living systems. They remind us that life is not merely a result of chance, but rather an intricate interplay of forces that have been at work for billions of years, revealing nature's remarkable ability to innovate and adapt. Abiogenesis is a fascinating concept in biology that explores how life might have originated from non-living matter in Earth's early history. This idea suggests that, under the right conditions, simple organic compounds could emerge and gradually lead to the formation of more complex life forms. Understanding abiogenesis opens a window into how beginnings can arise from what seems like nothing. At the heart of abiogenesis is the idea that life, as we know it, might have started from a primordial soup of simple molecules. These could have formed through various natural processes, such as lightning strikes or volcanic activity, which provided the energy needed to create these building blocks of life. Over time, these molecules could undergo a series of chemical reactions, eventually leading to the formation of amino acids, nucleotides, and other essential components of living organisms. One of the key experiments that supports this idea is the Miller-Urey experiment, conducted in the mid-20th century. Researchers simulated conditions of early Earth in a laboratory setting, exposing a mixture of gases to electrical discharges. They observed that a range of organic compounds, including amino acids, formed during the experiment. This highlighted the potential for simple elements to give rise to complex organic molecules without any direct biological influence. While the exact pathway to the origin of life remains a mystery, the exploration of abiogenesis fuels our understanding of life's beginnings. It encourages a sense of wonder about how life could emerge from a lifeless planet, suggesting that the building blocks of life are all around us, waiting for the right conditions to spark their transformation. This insight not only captivates our imaginations, but also encourages scientists to continue investigating the possibilities of life beyond Earth, where similar processes might be at play. Extinction, though often perceived as a negative event, plays a surprisingly significant role in shaping the dynamics of ecosystems. When a species goes extinct, it creates a gap in the ecological web. This absence can lead to new opportunities for other species, allowing for the emergence of new relationships and potential. In other words, the loss of one species can ignite a cascade of changes that ultimately supports the proliferation and adaptation of others. For example, when a predator species disappears, prey species may begin to flourish without the threat of being hunted. This sudden increase in population can alter the vegetation and other aspects of the habitat, creating conditions that may favor the growth of different species. New plants may thrive, which in turn can attract new herbivores or beneficial insects. These shifts often contribute to greater biodiversity, as new species take advantage of the resources that become available. Additionally, extinction can act as a catalyst for evolution. The empty ecological niches left behind can be filled by remaining species that evolve and adapt to the new conditions over time. This process, known as adaptive radiation, has led to significant diversity in various taxa throughout history. A prime example would be the evolution of mammals following the extinction of the dinosaurs, which paved the way for a remarkable variety of forms and adaptations. This intricate interplay between extinction and rebirth underscores the resilience of nature. While the immediate impact of extinction can be devastating, it also opens pathways for innovation within ecosystems, reminding us that life continuously adapts to changing circumstances. In many ways, it illustrates the delicate balance and interconnectedness of all living things, inviting us to ponder the wonders of ecological transformation. The universe is a fascinating tapestry of cycles and processes, many of which suggest a dynamic nature that could support the idea of creation from nothing. One prominent example is the life cycle of stars. These celestial bodies are born from vast clouds of gas and dust, undergoing nuclear fusion to light up the cosmos. When they exhaust their nuclear fuel, they meet dramatic ends, some through supernova explosions, which can scatter elements across the universe, while others may collapse into black holes. This cycle of birth, death, and rebirth demonstrates how matter can emerge from seemingly empty space, reinforcing the idea that creation can indeed stem from nothing. Moreover, the cosmic cycles extend beyond individual stars. On a grander scale, galaxies themselves evolve through a series of transformations. They can collide, merge, and form new structures, changing the overall landscape of the universe. These collisions often trigger the formation of new stars from the remnants of older galaxies. In this way, the universe continually recycles its materials, underscoring a theme of renewal and transformation. This continuous process suggests that what might seem like an end is often just a prelude to something entirely new, bringing to mind the concept that existence begins anew, even after apparent obliteration. Another cycle worth noting is the expansion of the universe, a phenomenon observed since the early 20th century. Galaxies are moving away from each other, indicating that the universe is continuously growing. The implications of this expansion invite contemplation about its origins. If everything we see was once concentrated into an infinitesimally small point before the Big Bang, the universe's ongoing expansion embodies a creation story that arises from nothing, evolving space where once there was none. Lastly, consider the cyclicity found in various theories of cosmology, such as the oscillating universe model. This posits that the universe undergoes infinite cycles of expansion and contraction. After each big crunch, where the universe collapses in on itself, conditions could reset, leading to another Big Bang. This notion of cyclical rebirth mirrors philosophical and spiritual ideas about creation, suggesting that our universe might be an eternal cycle of coming into existence and fading into nothingness, a testimony to the profound and mysterious ways in which creation can unfold from nothing. Theories of rebirth in the universe, often referred to as cyclic or oscillating models, suggest that the universe undergoes endless cycles of expansion and contraction. This idea brings us to the fundamental concept of nothing. In physics and cosmology, nothing is not merely the absence of everything. Instead, it represents a state that can be paradoxically rich in potential. The idea of the universe rebirthing itself raises profound questions about what it means to be and not to be. In cyclic models, after the universe reaches its maximum expansion, it begins to contract under the force of gravity. This contraction eventually leads to a singularity, a point where all known physical laws cease to function as we understand them. At this stage, one might wonder whether the universe is returning to nothingness, only to burst forth again in another Big Bang. This cyclical nature suggests that even in apparent nothingness, there exists the potential for rebirth, an ongoing cycle of creation and destruction. Furthermore, these concepts challenge our traditional views on existence itself. If the universe does indeed oscillate between phases of existence and non-existence, it implies that nothing is somehow a precursor to something. This presents a fascinating philosophical perspective wherein what we consider nothing is not a void, but rather a fertile ground for new beginnings. Ultimately, the interplay between the cosmos, time, and the notion of nothing offers a jagged yet fascinating glimpse into the nature of reality. As our understanding of these theories grows, so too does our appreciation of existence and the universe's incredibly complex lifetimes. Each cycle may represent the universe reflecting on its past, while forging paths into what will come, a grand cosmic dance that echoes the fragile boundary between existence and non-existence. The idea of personal rebirth often runs parallel to the concept of universal origins in fascinating ways. Both concepts emphasize transformation and renewal. In our lives, personal rebirth can take place during significant events, such as overcoming hardship or experiencing profound moments of inspiration. This concept of transformation can be likened to how the universe began, emerging from a singularity in a tremendous explosion of energy and matter, known as the Big Bang. Just as individuals navigate their own journeys of growth, the universe itself has gone through a vibrant process of evolution. When we think about universal origins, it often conjures images of vast cosmic events, yet it holds deep resonance with the human experience. Every atom in our bodies originated from stars that lived and died long ago, imbuing us with an intrinsic connection to the cosmos. Our personal transformations, similar to those universal shifts, reflect both endings and new beginnings. Life lessons learned through struggle or enlightenment can mirror the birth of new galaxies in the expansive universe, each leading to a fresh chapter in their respective stories. Moreover, both personal rebirth and the unfolding history of the universe carry a sense of interconnectedness. Humans ponder their place in the grand scheme of things, recognizing that solar systems and galaxies, just like individuals, evolve through cycles of birth, death, and regeneration. In the same way that one experiences a renewed sense of purpose or identity, the cosmos is also in perpetual motion, continually reshaping and redefining itself through forces of physics and time. In reflecting on these parallels, we uncover a deeper layer of understanding about our lives and the universe. The continuous cycle of transformation, whether it be personal or universal, inspires wonder and encourages us to embrace change. As we explore our origins, we also recognize the shared heritage that connects every living being and the cosmos around us, reminding us of both our smallness and our magnificent potential within this vast universe. String theory presents a fascinating perspective on the origins of our universe, suggesting that what we perceive as reality may actually emerge from the fabric of nothingness. At its core, string theory posits that the fundamental building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny vibrating strings. These strings can manifest in different vibrational modes, and it is these variations that give rise to the diverse particles and forces we experience. In this framework, the concept of nothing is not mere emptiness. Instead, it refers to a quantum vacuum state, a dynamic, fluctuating arena filled with energy and potential. Even in this seemingly void space, particles can spontaneously pop in and out of existence, creating a backdrop of possibilities. String theory suggests that the energies and interactions of these strings in this quantum vacuum could lead to the formation of the universe as we know it. Emerging from this fabric of nothingness, our universe could be seen as a multidimensional structure, with extra dimensions that our senses cannot perceive. This implies that the three dimensions of space, along with time, are just a small part of a much broader reality. Instead of a single universe, string theory hints at a multiverse where countless other universes could exist, each with its own unique properties, waiting to be discovered. The notion of all that exists arising from nothing challenges our everyday understanding of creation and existence. It opens the door to profound questions about the nature of reality and the boundaries of scientific inquiry. Is it possible that the universe is a transient spark in an ever-active quantum sea? String theory thus invites us to ponder the extraordinary ways the universe might have come into being, with only the enigmatic vibrations of strings echoing through the void. The Higgs field is a fundamental aspect of our universe, acting as a sort of cosmic molasses that fills all of space. This mysterious field plays a crucial role in how particles acquire mass, which is often described as one of the most significant breakthroughs in modern physics. According to the standard model of particle physics, the Higgs field interacts with particles as they move through it, similar to how a swimmer feels resistance when moving through water. When particles like electrons move through the Higgs field, they experience a resistance or drag, which manifests as mass. Without this interaction, these particles would essentially zip around at the speed of light and would not have the mass needed to form atoms, molecules, or any matter that makes up our universe. Essentially, the Higgs field endows particles with the property of mass, which is fundamental to the structure of everything around us. Now, when scientists first proposed the existence of the Higgs field, it was met with skepticism. For many years, the Higgs boson, the particle associated with this field, remained elusive. However, in July of 2012, the world celebrated the confirmation of its existence at CERN's Large Hadron Collider. This was a pivotal moment, as it provided crucial evidence supporting the theory that the Higgs field permeates the universe and is responsible for the mass we observe. The Higgs field allows particles to acquire mass through their interactions with it. Without this field, our reality would be vastly different, lacking the structure and complexity that we often take for granted. The discovery of the Higgs boson not only affirmed the existence of this field, but also opened new doors in our understanding of the universe, revealing the intricate workings behind the familiar phenomena of mass and matter. The concept of entropy is fundamental to understanding the universe's evolution and the flow of time. At its core, entropy measures the level of disorder within a system. In simple terms, systems tend to move from order to disorder, meaning that over time things naturally evolve toward a state of greater entropy. This idea is crucial when contemplating how everything began from what we refer to as nothing. In the event known as the Big Bang, the universe originated from an extremely hot and dense state. At that moment, entropy was remarkably low, creating a highly ordered environment. As the universe expanded and cooled, it began to develop structure, from the formation of stars and galaxies to the complex interactions that occur in nature today. This transition illustrates how that initial low-entropy state gradually evolved into a more complex arrangement, with regions of low entropy forming amidst an overall trend of increasing disorder. Interestingly, this increase in entropy has profound implications for our understanding of time. The second law of thermodynamics asserts that entropy in a closed system will always increase over time, creating a directionality to the flow of time that we experience. Consequently, as entropy grows, our universe moves forward, leading us from a very ordered beginning into the vibrant, dynamic, and sometimes chaotic reality we see today. Thus, the relationship between entropy and the origins of the universe invites us to reflect on the fundamental nature of existence itself. Everything that exists, from the smallest particles to the grandest galaxies, is an expression of the shift from that initial low-entropy state to the beautifully complex yet increasingly disordered universe we inhabit. The journey from nothing to everything is not just a story of creation, but also a narrative steeped in the intimate dance of order and chaos. The cyclical universe model presents a fascinating perspective on the origins and fate of the cosmos. According to this theory, the universe does not have a singular beginning or end, as traditionally thought with the Big Bang model. Instead, it undergoes an infinite series of expansions and contractions. Each cycle begins with a Big Bang, evolves through an expansive phase, and eventually leads to a collapsing phase, culminating in what might be termed a big crunch. This cycle could repeat indefinitely, suggesting a universe that is eternally reborn. One of the profound implications of this model is how it reshapes our understanding of time itself. In a cyclical universe, time may not be linear as we often perceive it, but rather a more complex, looping construct. The idea of beginnings and ends could take on new meanings, as every cycle leads back into another, challenging our conventional concepts of birth and demise. This perspective encourages deeper philosophical reflections on existence, continuity, and the nature of reality itself. Additionally, if the universe is cyclical, it raises compelling questions about the nature of cosmic information and matter. Each cycle might carry forward remnants from previous universes, potentially influencing the conditions in which new stars, planets, and even life forms emerge. This hints at an interconnectedness across cosmic time, where every event and every entity may inherit hints or echoes from earlier epochs, creating a rich tapestry of existence that transcends a single moment of creation. Ultimately, a cyclical universe model not only broadens our understanding of the cosmos, but also ignites our curiosity about the fundamental forces at play. It invites exploration into concepts of entropy, the role of dark energy, and the potential for life across different epochs. As we ponder these ideas, we embrace the wonder of a universe that may be far more complex and intertwined than we could ever imagine, fundamentally linked through cycles of creation and collapse. The laws of thermodynamics provide a fascinating lens through which to explore the concept of beginnings, especially the idea of creation from a void. At the core of these laws lies the principle that energy cannot be created or destroyed, only transformed from one form to another. This fundamental truth raises intriguing questions about the origins of the universe. If energy was always present in some form, could the universe have emerged from a state of nothingness or void? The first law of thermodynamics, often referred to as the law of energy conservation, suggests that the total energy of an isolated system remains constant. This implies that the universe's energy existed in some capacity before the Big Bang. The second law introduces a concept of entropy, or disorder. Over time, systems naturally progress toward greater disorder. Initially, this might seem counterintuitive when considering creation, as beginnings often suggest order, the emergence of stars, planets, and life. However, the profound implications of thermodynamic laws lie in their challenge to the idea of absolute nothingness. Instead of an empty void, some scientists suggest that the universe may have originated from a quantum state, a form of energy with potential yet to be realized. In this sense, the so-called void was teeming with fluctuations that could ultimately give rise to the cosmos we see today. This idea aligns with the notion that beginnings are not simply about the emergence of something from nothing, but rather the manifestation of energy in new forms. Ultimately, thermodynamic laws encourage us to think deeply about beginnings. They guide our understanding of how energy and disorder interact in the cosmos, leading to the diverse and complex structures we observe. While we may not fully grasp these origins, the interplay of energy and entropy provides a framework that hints at the profound connections between void and creation, a story still unfolding in the grand tapestry of the universe. The idea that nothing can yield everything is profound and has captivated scientists and philosophers for centuries. At the heart of this concept lies quantum mechanics, a branch of physics that explores the behavior of the smallest building blocks of our universe. In quantum physics, so-called quantum fluctuations can cause particles to appear and disappear spontaneously in a vacuum, which is often described as nothing. This phenomena suggests that even the emptiest space teems with potential, challenging our traditional understanding of nothingness. Additionally, the concept of cosmic inflation supports this idea. After the Big Bang, the universe underwent a rapid expansion that smoothed out any initial irregularities. This model posits that tiny fluctuations in energy during this inflationary period could have led to the formation of galaxies and large-scale structures we see today. The interplay between these quantum fluctuations and the expansive nature of the universe indicates that what appears to be nothing, a vacuum, can indeed give rise to everything we observe around us. On the other hand, some arguments counter the notion that nothing can create everything. Critics point to the need for underlying laws and conditions that govern quantum behavior. For example, if nothing can lead to particles, there must be some form of quantum field underpinning that event. This suggests that true nothingness, devoid of any pre-existing rules or parameters, may not actually exist in a way we can comprehend. Anyone seeking to demystify existence must reckon with how these foundational elements shape reality. The philosophical implications of these scientific insights are equally fascinating and spark vibrant discussions about the nature of existence. Can we embrace a universe that sprang from nothing, or does this nothing contain untold complexities of its own? As our understanding of physics continues to evolve, so too does our grasp of these abstract concepts, weaving a rich tapestry that connects the fabric of the universe to the enigma of our own existence. The anthropic principle offers a fascinating perspective on the cosmos and our place within it. At its core, this principle suggests that the universe's laws and constants are precisely tuned for the existence of life, particularly human life. In a way, it posits that our ability to observe the universe dictates how we understand it. If the universe were even slightly different, it might not support life as we know it. Hence, the very fact that we are here to question and contemplate our existence implies a specific set of circumstances that made our reality possible. This principle helps to shape discussions about how everything emerged from seemingly nothing. Scientists ponder how the universe began approximately 13.8 billion years ago with the Big Bang. Before that event, it is theorized that all matter and energy were in a hot, dense state. The anthropic principle suggests that the conditions following the Big Bang were not just random. Instead, they were conducive to the formation of stars, galaxies, and eventually planets, creating environments capable of harboring life. When we consider the vastness of the universe, with billions of galaxies and potentially countless planets, our existence seems incredibly improbable. Yet the anthropic principle suggests that multiple universes could exist, each with different physical laws and constants. In this broader context, our universe is one that happens to have the right conditions for life to emerge. It invites reflection on the idea that while the emergence of everything from nothing appears astonishing, the very nature of our universe supports our presence to ask such profound questions. The anthropic principle offers a narrative that connects existence with observation. It is a reminder that our reality, filled with complexity and wonder, arises from specific conditions that enable life. The mere fact that we are here to explore these concepts contributes to an understanding of how richness can arise from apparent simplicity, showcasing the extraordinary story of the universe's emergence from nothing into everything we recognize today. Neutrinos and fundamental particles are like mysterious messengers from the infancy of the universe, carrying vital clues about its origins. When we look back at the earliest moments after the Big Bang, temperatures were so high that only fundamental particles could exist in that chaotic environment. Neutrinos among these played a significant role in the processes that shaped the universe. Their feeble interactions make them difficult to detect, but they provide invaluable information about conditions in those early moments. These elusive particles are created through various processes, including radioactive decay and nuclear reactions. In the early universe, as it began to cool, neutrinos were produced in vast quantities. Understanding their behavior and properties helps scientists piece together the timeline of events that followed the Big Bang. For instance, the neutrino background, which we can still observe today, is a remnant from when the universe became transparent to radiation. By studying this faint glow of neutrinos, researchers can infer details about the density and distribution of matter at that time. Moreover, fundamental particles serve as the building blocks of everything we see in the universe today. The interactions between these particles during the first few seconds are thought to have played a crucial role in how various elements formed. For example, understanding how protons and neutrons combine to form hydrogen and helium gives us insights into the processes that led to the creation of galaxies and stars billions of years later. Each particle's unique characteristics, such as mass and charge, offer hints about the fundamental forces that govern the early universe. In exploring the dynamics of neutrinos and fundamental particles, scientists can test theories of cosmic evolution and the fundamental laws of physics. This research not only reveals how the universe expanded and cooled, but also highlights the intricate patterns that formed the complex cosmos we inhabit today. Each discovery in this field unfolds before us like a story, revealing the magnificent and mysterious chapters of our universe's early creation. Advancements in particle physics have significantly deepened our understanding of what we might consider nothing. For centuries, nothing was simply thought of as an absence, an emptiness devoid of matter, energy, or any physical reality. However, through the lens of modern particle physics, we have come to realize that even the concept of nothing carries profound implications and complexities. At the smallest scales, quantum physics presents a picture of a vibrant cosmos rich with activity, even in apparent emptiness. Particle physicists have discovered that the vacuum of space is not merely a void. Instead, it is teeming with virtual particles that briefly pop in and out of existence. These fleeting particles arise from energy fluctuations in the vacuum itself, challenging our traditional notions of emptiness, suggesting that nothing is brimming with potential. Additionally, experiments at particle accelerators, such as the Large Hadron Collider, have illuminated the mysterious nature of dark matter and dark energy. Together, they make up nearly 95% of the universe's total content. While we cannot directly observe dark matter, its existence is inferred from gravitational effects on visible matter. This opens up an exciting dialogue about how nothing can possess properties that influence the universe at a fundamental level, reshaping our understanding of cosmological phenomena. Ultimately, advancements in particle physics compel us to confront the complexities of nothingness. This deeper understanding not only reshapes our philosophical inquiries into existence, but also paves the way for further explorations in cosmology. As science continues to unravel the intricacies of the universe, nothing may turn out to be one of the most captivating subjects in the grand narrative of our cosmos. In quantum mechanics, the vacuum state is often misunderstood as an empty void. However, this perspective misses the profound complexity of what a vacuum really represents. Instead of being devoid of activity, the vacuum state is teeming with energy and potential. It serves as a baseline or ground level of a quantum field, where particle pairs can spontaneously appear and disappear thanks to the inherent fluctuations in energy that define quantum behavior. These fluctuations allow for momentary creations of particle-antiparticle pairs, which borrow energy from the vacuum itself. This phenomenon is permitted by the principles of quantum mechanics, particularly Heisenberg's uncertainty principle, which allows for temporary changes in energy levels. Thus, in this framework, the vacuum isn't truly empty. It's a bustling, dynamic space filled with potential activity, constantly fluctuating at the quantum level. Moreover, this interpretation plays a crucial role in our understanding of the universe's evolution. When the universe was incredibly young, its vacuum state was a hotbed of energetic activity. Quantum fluctuations seeded the very structure of galaxies and cosmic features we observe today. Theories like cosmic inflation suggest that it is through the influences of vacuum states that the cosmos expanded rapidly, transitioning from a minuscule point to the vast universe we inhabit. Ultimately, the vacuum state is not merely a backdrop, but an active player in the creation and evolution of our universe. It serves as a foundation for understanding particle physics and cosmology, revealing that even in the depths of emptiness, there exists a rich tapestry of potential waiting to unfold. The transition from nothing to everything is one of the most profound questions in cosmology, and different models offer various interpretations of this mysterious process. At the heart of many cosmological theories is the Big Bang, which posits that the universe began as an incredibly hot, dense point about 13.8 billion years ago. This model suggests a rapid expansion that created space itself, along with energy and matter. It raises the question of what came before the Big Bang, leading to diverse viewpoints among scientists. One notable interpretation is rooted in quantum mechanics, which proposes that nothing is not merely an absence, but can be a state filled with potential. In quantum field theory, particles can spontaneously appear and disappear, suggesting that universes might arise from quantum fluctuations in a vacuum. Some theorists, like Alan Guth, suggest that our universe could be just one of many, forming in a vast multiverse where varying conditions allow for an infinite variety of universes to emerge, each with its own unique structure and laws. Another perspective comes from string theory, which posits that fundamental particles are not point-like, but rather tiny vibrating strings. This model suggests that the universe's initial conditions could involve higher dimensions and complex geometric shapes that we have yet to fully comprehend. Within this framework, our universe might have emerged from a pre-existing state influenced by higher dimensional interactions that bore it into existence. Lastly, there are philosophical angles to consider as well. Some interpretations propose that the universe might not have a singular beginning, but could be eternal, cycling through phases of expansion and contraction. This view challenges us to rethink our understanding of time and existence itself. Each model, with its unique strengths and weaknesses, leads us to ponder the intricate dance of creation, decay, and rebirth in the cosmos, inviting us to marvel at the journey from nothing to everything. The standard model of cosmology, often termed the lambda cold dark matter model, operates on several foundational assumptions about the fabric of the universe, even regarding the concept of nothing. One of the core presuppositions is that the universe is isotropic and homogeneous on large scales. This means that when we look at the universe from a great distance, it appears essentially the same in every direction, and there are no preferred locations. This uniformity simplifies our understanding of cosmic structures and their origins. Furthermore, this model assumes that space itself is expanding. The discovery of the universe's expansion, fueled by observations of distant galaxies and their redshifts, led cosmologists to part ways with the idea of a static universe. This expansive vision invites questions about the nature of nothing, as it relates to the voids between galaxies and the energy dynamics that underlie their movement. As the universe expands, it also implies that there was a point in time when it was extremely dense and hot, a state often referred to as the Big Bang. Additionally, when we speak of nothing in the context of cosmology, we must consider the nature of the vacuum. In quantum field theory, empty space is not truly empty. Instead, it is often filled with fluctuating energy fields and virtual particles. This nuances the idea of nothing and challenges our intuition about the vacuum as being merely an absence of matter. Thus, in cosmology, nothing can be quite complex, hinting at a rich landscape of physical phenomena lurking beneath a seemingly empty canvas. Finally, the assumptions of the Standard Model also embrace the concept of dark energy as a driving force behind the universe's accelerated expansion. Dark energy constitutes a significant portion of the universe's total energy density, yet it remains elusive and largely mysterious. This ongoing inquiry has profound implications for our understanding of nothing, pushing the boundaries of knowledge and inviting us to explore deeper questions about existence and the universe's fate. The Standard Model's assumptions regarding nothing delve into fundamental truths about the nature of our universe, igniting curiosity about what lies beyond our observational limits. Cosmology, the study of the universe's origins and structure, has been dominated by mainstream theories like the Big Bang. However, several alternative theories present compelling challenges that encourage us to re-evaluate our understanding of the cosmos. One notable alternative is the steady-state theory, which proposes that the universe is eternal and unchanging on a large scale, suggesting that new matter is continuously created as the universe expands. This differs significantly from the Big Bang, which depicts a beginning point. Another interesting perspective comes from loop quantum gravity. This theory posits that the fabric of space and time is quantized, incorporating insights from quantum mechanics. Unlike the traditional view of a singular explosive event at the universe's origin, loop quantum gravity suggests that the universe could undergo cycles of expansion and contraction, leading to a dynamic and continuous universe that has no definitive beginning or end. There are also ideas rooted in the concept of multiverses, where our universe is just one of many, each with its own unique properties and dynamics. This challenges the notion of a singular origin by suggesting that what we perceive as the universe is merely one bubble in a much larger cosmic foam. This idea raises profound philosophical questions about the nature of existence and what it means for our understanding of life. Finally, these alternative theories often intersect with concepts in dark matter and dark energy, which remain largely mysterious in the mainstream narrative. By challenging conventional wisdom, these cosmological theories not only provide fresh frameworks for discussing the universe's origins, but also invite us to explore the limits of our current scientific knowledge and imagination. Each theory, in its own way, enriches the fascinating dialogue about what lies beyond our current understanding of the cosmos. The concept of a static universe has long been a fascination for scientists and philosophers alike. This idea suggests that the universe is unchanging and eternal, and can be imagined as a vast, unyielding expanse where stars and galaxies exist in a timeless state. Early in the 20th century, thinkers like Albert Einstein were drawn to this model, believing that the universe did not require a beginning or an end, operating instead in a state of perpetual equilibrium. Contrasting sharply with the notion of a static universe is the idea of nothingness. This concept proposes a universe devoid of substance, energy, or even the framework of time itself. The idea of nothingness challenges us to contemplate what it means for something to exist at all. If we take this concept seriously, we realize that the very act of existence seems to defy the implications of nothingness, suggesting that the universe is not static, but instead dynamic and evolving. As we progressed into the 20th century, new discoveries in cosmology unraveled the notion of a static universe. The observation that galaxies are moving away from us, which Edwin Hubble famously described, introduced the idea that the universe is expanding. This revelation led to the widely accepted Big Bang theory, where the universe originated from a singular point and has been growing ever since. Thus, rather than a static expanse, we envision an ever-evolving cosmos rich with the history of its formation and subsequent expansion. The tension between a static universe and the idea of nothingness stirs exciting questions about existence itself. While a static universe offers a picture of constancy, theories involving nothingness prompt us to consider the miraculous nature of creation and change. As we delve deeper into cosmic explorations, we find ourselves navigating the fascinating waters between what it means to exist and the profound mystery of what might lie beyond existence itself. Throughout history, several key scientists have profoundly influenced our understanding of nothing and its role in the creation of the cosmos. One of the earliest figures in this conversation is the ancient philosopher and mathematician Pythagoras, often noted for his belief that numbers and mathematical concepts underpin reality. He suggested that voids or empty spaces were just as essential to existence as the material world itself, laying early groundwork for the idea that nothing has a significant role. Fast forward to the 17th century, and we encounter the groundbreaking work of Isaac Newton. His laws of motion and universal gravitation reshaped our perception of space and matter. Newton introduced the idea of a vast, empty space in which objects exist and interact, challenging previous notions that space was predetermined or filled with ether. His concept of absolute space allowed for the idea that nothingness could exist independently, enabling celestial bodies to move freely within it. In the 20th century, Albert Einstein transformed our understanding of space and time with his theory of relativity. He proposed that space is not merely an emptiness, but a dynamic entity that is affected by the presence of mass. Einstein's view introduced a new perspective on nothingness. It is not a mere void, but an active participant influenced by energy and matter, fundamentally interwoven with the fabric of the universe. Adding to this conversation, quantum physics emerged in the early 20th century, revealing that even in what we perceive as nothing, enormous fluctuations and activities are taking place at the subatomic level. Scientists like Niels Bohr and Werner Heisenberg showed that empty space is filled with potential and uncertainties. This suggests that rather than being a passive background, nothingness plays an instrumental role in the creation and evolution of the universe, leaving us with questions about the fundamental nature of reality itself. Cosmic dynamics plays a crucial role in revealing the origins and evolution of the universe, shaping everything from the tiniest particles to the grand structure of galaxies. At its core, cosmic dynamics refers to the interactions and movements of celestial bodies influenced by gravitational forces. Understanding these dynamics allows scientists to piece together the chronology of events that led to the birth of the universe and its ongoing development. The Big Bang theory serves as a foundation for understanding cosmic dynamics. It posits that the universe began as an infinitely small, hot and dense point around 13.8 billion years ago. From that point, space itself began to expand rapidly in a cataclysmic explosion, spreading energy and mass throughout the cosmos. This initial expansion laid the groundwork for all subsequent movement and formation of matter, leading to the creation of fundamental particles and, eventually, the atoms that make up stars and planets. As the universe expanded, the interplay of gravity and motion became vital in the formation of structures like galaxies. Cosmic dynamics explains how matter clumped together under its own gravitational influence, forming the stars and galaxies we see today. Over billions of years, these structures have evolved, merging and interacting, leading to phenomena such as supernovae, black holes, and the creation of new stars. Cosmic dynamics provides a continuous thread connecting the past to the present, showcasing how the elements that compose us were forged in the hearts of stars. Ultimately, our understanding of cosmic dynamics reveals more than just the evolution of celestial bodies. It reflects the interconnectedness of all matter and energy in the universe. By studying how galaxies move and interact, scientists glean insights into dark matter, dark energy, and the very fate of the universe itself. This profound interplay between dynamics and evolution invites us to ponder our place in this grand cosmic tapestry, emphasizing that we are not just observers, but part of the universe's ongoing story. Observational evidence plays a crucial role in shaping our understanding of the cosmos and its origins. When scientists propose different models of cosmic beginnings, like the Big Bang theory or the theory of eternal inflation, they rely heavily on data collected from various sources in the universe. This evidence helps to confirm or refute these models, allowing for a clearer picture of how the universe came into being. One of the most significant pieces of observational evidence is the cosmic microwave background radiation. This faint glow, permeating the universe, is a remnant of the heat from the very early universe, and it provides a snapshot of the universe when it was just about 300,000 years old. Its uniformity and slight fluctuations align remarkably well with predictions made by the Big Bang theory, lending substantial support to this model. Scientists continuously study this background radiation to glean insights about the conditions present at the universe's inception. Additionally, the movement of galaxies offers another vital clue. Observations show that galaxies are generally moving away from each other, which suggests that the universe is expanding. This phenomenon is consistent with the predictions of the Big Bang theory and serves as a powerful piece of evidence against static models of the universe. Further analysis of galaxy redshifts helps us better understand the rate of this expansion and how it has changed over time. Observational evidence serves as the backbone of cosmological theories. It allows scientists not only to test their ideas, but also to refine them continually. As new technologies enable deeper exploration of the universe, we gain even more data that challenges existing models, pushing the boundaries of our knowledge and understanding of cosmic beginnings. Each observation deepens our appreciation for the complexity of the universe and the intricate dance of its beginnings. The flatness of the universe is a concept that refers to the geometric nature of space on a cosmic scale. In simple terms, when cosmologists say the universe is flat, they mean that the rules of geometry we learn in school, like the angles in a triangle adding up to 180 degrees, hold true at vast distances in space. This flatness emerges from the idea that the average density of matter and energy in the universe is precisely at a critical value, where the universe expands forever, but at a slowing rate. This critical density leads to fascinating discussions about the very fabric of existence, everything and nothing. When cosmologists explore the ultimate fate of the universe, they ponder whether it will continue expanding indefinitely, slow down, and eventually recollapse, or settle into a steady state. Each of these scenarios challenges our understanding of everything that exists. In a flat universe, however, the endless expansion makes it seem as if there is always more nothing to explore beyond the edges of our observable universe, raising profound questions about what lies beyond our perception. Furthermore, the flatness of the universe suggests that it may be a part of a much larger, perhaps infinite space. This consideration leads us to think about infinity and the origin of all things, how everything that exists might emerge from what we perceive as nothing. The relationship between the concepts of everything and nothing becomes a philosophical reflection on existence itself. It compels us to acknowledge that our universe, in all its complexity, arose from conditions that may not have had any physical properties at all. The flatness of the universe serves as a gateway into profound philosophical discussions about the nature of reality. As we delve deeper, we realize that our understanding of everything is intricately linked to the mysteries of nothingness. This delicate balance fuels a sense of wonder, encouraging us to explore the origins and fate of our universe while appreciating the enigmatic connection between the things we can measure and the vast unknown that surrounds us. Recent discoveries about exoplanets, those planets outside our solar system, have significantly expanded our understanding of where and how life might arise in the universe. With advancements in technology, astronomers have identified thousands of these distant worlds, many of which exist within what is known as the habitable zone. This is the region around a star where conditions might be just right for liquid water to exist, a critical ingredient for life as we know it. The sheer diversity of exoplanets has prompted scientists to rethink the conditions required for life. Some exoplanets are located in environments radically different from Earth, including those with extreme temperatures and a variety of atmospheric compositions. These discoveries hint that life could potentially thrive in forms and places we had never imagined. For example, researchers are considering life that could exist in methane-rich atmospheres or in the harsh conditions of tidally locked planets, where one side perpetually faces their sun. Moreover, by studying the atmospheres of some exoplanets, scientists have detected signs of chemical activity that could indicate biological processes. Gases such as oxygen, methane, and carbon dioxide found in the right ratios might suggest that a planet is not just geologically active, but potentially alive. These findings fuel the ongoing search for biosignatures, substances that point to the presence of life beyond Earth. As we learn more about the variety of environments that exoplanets provide, we refine our models of life's origins. The realization that life could adapt to a wide range of conditions illuminates our understanding of how life began on Earth. It encourages scientists to explore and question what life means, pushing the boundaries of our knowledge and possibly leading us to discover life forms that are completely different from the ones we know today. The narrative of creation from nothing has long been a cornerstone of human thought, merging theology, philosophy, and science. With each scientific advancement, our understanding of the universe's beginnings has become more nuanced. In the past, the concept of spontaneous creation from nothing was often viewed as purely a philosophical or theological debate. However, discoveries in cosmology and physics have introduced profound insights into how we perceive the origins of everything we see around us. For instance, the Big Bang theory has reshaped our understanding of the universe's inception. According to this theory, about 13 billion years ago, the universe began as an inexplicably dense and hot point, rapidly expanding to create everything from galaxies to stars. This suggests that rather than a simple act of creation from nothing, the universe evolved from an initial singularity. It compels us to reconsider what nothing means in a cosmological context. Could it be that this nothingness was filled with potential energy, waiting to manifest as the universe? Moreover, advancements in quantum physics have introduced the notion that particles can appear and disappear, seemingly from nothing. This has led to discussions about the vacuum of space, which is often thought to be empty. However, today's understanding reveals that a vacuum is teeming with virtual particles, oscillating in and out of existence. This challenges our definitions of creation and existence. If something can arise from a vacuum, does that alter our perceptions of creation from nothing, or redefine the very idea of nothing itself? These scientific breakthroughs offer us not just answers, but more questions, encouraging a deeper exploration into the origins of the universe. The narrative of creation is continuously evolving, reflecting humanity's insatiable curiosity about existence. Each step forward in scientific understanding opens new doorways, paving the way for a richer, more intricate story of how everything began. And while we might not yet have all the answers, the ongoing dialogue between science and philosophy will undoubtedly enrich our appreciation of the cosmos and its mysteries. Energy is a fundamental aspect of our universe, serving as the engine that drives all transformations, from the smallest particles to the vastness of galaxies. When we delve into the transformation of nothing into everything, we often encounter the concept of energy in a fascinating light. At its core, energy is the capacity to do work or produce change, and it permeates every corner of the cosmos. In the earliest moments after the Big Bang, the universe began in a state that we often describe as nothing, a hot, dense state filled with energy. As this energy expanded, it fueled the creation of matter. According to the principles of physics, energy can convert into matter and vice versa, encapsulated in the famous equation by Albert Einstein, which tells us that energy and mass are interchangeable. Thus, during the universe's expansion, energy could give rise to particles, leading to the formation of atoms, and eventually, everything we observe today. Furthermore, energy plays a pivotal role in the life cycle of stars, which are the architects of the universe. Inside a star, nuclear fusion transforms hydrogen into helium, releasing vast amounts of energy in the process. This energy not only powers the star, but also contributes to the creation of heavier elements. When stars reach the end of their lives and explode in spectacular supernovae, they scatter these elements throughout space, seeding new stars, planets, and even the building blocks of life itself. By understanding the role of energy, we appreciate how a seemingly empty void can transition into a rich tapestry of existence. From cosmic events to the forces that shape our everyday lives, energy is the invisible thread that weaves everything together, highlighting the profound interconnectedness of all things in our universe. The concept of energy conservation is a fundamental principle in physics, stating that the total energy in a closed system remains constant over time. This principle has profound implications, especially when we consider the origins of the universe and ultimately everything we see around us. In the grand landscape of cosmology, the idea suggests that energy cannot be created or destroyed, only transformed. Delving deeper into the origins of the universe, scientists often look to the Big Bang. At this moment, around 13.8 billion years ago, All energy and matter were concentrated into an extremely hot and dense point. As the universe began to expand, that energy transformed into various forms, leading to the creation of particles, elements, and eventually stars and galaxies. This process illustrates energy conservation beautifully. The initial energy of the universe evolved over time into intricate structures while adhering to the overarching law of conservation. As the universe cooled and expanded, energy took on new roles. For instance, some of that energy became kinetic, driving the movement of celestial bodies. Other energy was transformed into radiation, which fills our universe today. This interplay of energy forms shaped not only cosmic structures, but also the very elements necessary for life, indicating that energy conservation has been a critical thread in the story of cosmic evolution. Interestingly, the implications extend into the realms of modern physics, where concepts like dark energy and the energy density of the universe challenge our understanding of how energy interacts in the cosmos. As we continue to explore these ideas, we uncover the delicate balance of energy transformations that have facilitated the creation of everything we know, further emphasizing that the story of our universe is intricately tied to the unchanging law of energy conservation. At the Large Hadron Collider at CERN, scientists conduct high-energy particle collisions to uncover secrets about the universe's fundamental building blocks. One of the most fascinating insights gained from these experiments is the ability to observe particle creation in ways that brush against the idea of creating matter from nothing. When two high-energy protons collide, their kinetic energy can transform into mass, giving rise to new particles. This phenomenon aligns with Einstein's famous equation, which tells us that energy and mass are interchangeable. During these collisions, scientists may witness the fleeting existence of particles that ordinarily would not exist in the stable conditions of our everyday universe. For instance, the discovery of the Higgs boson in 2012 helped illuminate how particles acquire mass. The Higgs boson itself is an example of a particle that came into being through energy conversion during these violent collisions. Such findings suggest that the universe is far more dynamic and pliable than one might assume, with particles popping in and out of existence, even if only for the briefest moment. Moreover, these collisions hint at processes that may have occurred just after the Big Bang, a time when energy densities were incredibly high. In that initial instant, the universe was a hot, chaotic place where energy could coalesce into matter. By recreating similar conditions in the lab, researchers can glean insights into how this early universe may have evolved and how matter as we know it came to be. It's a sort of window into the early moments of our cosmos. Ultimately, the work at CERN does not just expand our knowledge of particle physics, but also challenges our understanding of existence itself. By probing the conditions under which matter can appear, scientists continue to explore profound questions about the origins of the universe and our place within it. Each collision adds a piece to the puzzle of how energy transforms into the matter that constitutes everything around us, including ourselves. In the realm of quantum physics, there exists a fascinating concept known as quantum fields. At the most fundamental level, everything we perceive in our universe arises from these fields. Imagine a vast and intricate ocean, where all particles are like waves rising and falling. This ocean is ever present, even in what appears to be empty space. It turns out that this so-called void is not actually empty. Rather, it is a seething brew of activity. Fluctuations in these quantum fields illustrate how particles can emerge from this apparent nothingness. When energy levels fluctuate, the fields momentarily manifest excitations. These excitations can produce particles, such as electrons or photons, which are the very fabric of our universe. This phenomenon is often described with the phrase vacuum fluctuations, emphasizing that even in a vacuum, where no visible matter exists, the quantum world is teeming with potential. This process challenges our classical perceptions of reality. We typically think of particles as individual entities, but quantum fields suggest that particles are merely localized manifestations of something more profound. When we observe a particle, we are witnessing a peak in one of these fields, a snapshot of a transient fluctuation. This idea has profound implications for how we understand the creation of matter and the nature of existence itself. Thus, through these quantum fluctuations, the universe reveals a remarkable truth. The interplay of energy and fields can generate particles, even from what seems like emptiness. It is a reminder that the universe is full of surprises, where the line between existence and non-existence is far more blurred than we might ever imagine. Each moment is a dance of possibility, perpetuating the wonder of a reality that is far more intricate than it seems. Gravitational waves are ripples in spacetime caused by some of the universe's most energetic events, such as merging black holes or colliding neutron stars. Their discovery has opened a new window into the cosmos, and they play a vital role in enhancing our understanding of the universe's beginnings. These waves travel vast distances undeterred by matter, carrying information about their origins from billions of light-years away, a fact that has profound implications for cosmology. One of the most exciting aspects of gravitational waves is their potential to unveil conditions present during the Big Bang. Researchers can study these waves to gain insights into the early universe, particularly during a period known as cosmic inflation. This brief moment, occurring fractions of a second after the Big Bang, is theorized to have caused an extraordinary expansion of the universe. If gravitational waves can be detected from that era, they could provide evidence supporting or challenging existing theories about how the universe evolved. Moreover, the patterns and characteristics of gravitational waves can give us clues about the types of astronomical bodies that produced them during significant events, helping scientists piece together the timeline of cosmic history. By analyzing these waves, researchers have been able to test theories of gravity and cosmology that have stood for decades. This intricate dance of data could even reveal hints about dark matter or energy, those mysterious components believed to compose most of the universe, but remaining elusive in traditional observational astronomy. As we continue to refine our capacity to detect and analyze gravitational waves, our understanding of the universe's early moments expands ever more. This frontier of astrophysics might unravel some of the greatest mysteries and add further depth to our knowledge of how everything around us came into being, offering an exhilarating glimpse into the cosmos's profound origins. Entropy is a fascinating concept that helps illuminate the transformation from nothingness to the complexity of everything we see around us. At its core, entropy is a measure of disorder or randomness in a system. When we consider the universe, we see that it began in a remarkably ordered state during the Big Bang. At that moment, all matter and energy were concentrated in an incredibly small point, exhibiting low entropy. However, as the universe expanded, things began to change dramatically. As time unfolded, the universe evolved and structures began to form. Stars and galaxies emerged, creating pockets of order amidst the vast cosmic landscape. This transition illustrates a fundamental truth. While local regions of the universe can exhibit decreasing entropy, the overall trend remains an increase in entropy. Although stars burn brightly, creating order within their nuclear fusion processes, they ultimately release heat and energy, contributing to a greater disorder in the universe at large. This balance of local order and universal disorder is at the heart of understanding entropy. Moreover, entropy is significant in comprehending the life cycles of stars. A star spends most of its life in a state of equilibrium, fusing hydrogen into helium. This process creates a relatively ordered system with a consistent output of energy. However, once the hydrogen runs out, the star evolves, leading to explosive events like supernovae, which scatter elements throughout space. These elements then contribute to the formation of new stars and planets, illustrating a continual cycle where the universe experiences both creating and destroying phases, driving the progression from simplicity to complexity. As we contemplate the cycle from nothing to everything, it's essential to recognize that entropy is fundamentally linked to the idea of change and evolution in the cosmos. Every step in the formation of galaxies, stars, and even life itself encapsulates this interplay of order and chaos. So, the next time you look up at the night sky, remember that the stunning, intricate structures you see are born from the dance of entropy, encapsulating the universe's story from its inception to its endless expansion. Dark energy is a fascinating concept that has significantly changed our understanding of the universe and its beginnings. Traditionally, the prevailing narrative about how the universe started revolves around the Big Bang, a moment when all matter and energy exploded into being from a singularity. For decades, this idea framed our understanding of cosmic evolution. However, the discovery of dark energy has added a new layer of complexity to this story. Dark energy is thought to make up around 70% of the universe. Its existence suggests that not only is the universe expanding, but the rate of that expansion is accelerating. This is a striking departure from earlier views, which envisioned a gradual slowing down of expansion over time due to gravitational pull. The presence of dark energy implies a cosmic force working against gravity, leading to ever-rapid expansion. This shift invites us to rethink not just how the universe is evolving, but also what the implications are for its beginning. Moreover, the concept of dark energy has raised profound questions about the fate of the universe. If it continues to drive the expansion, what does that mean for the eventual destiny of galaxies, stars, and even the universe itself? Some models suggest a future where galaxies drift apart, stars burn out, and the universe grows cold and dark. This perspective invites a re-evaluation of our early narratives, where the beginnings of the universe may also be linked to this ongoing dynamic process of expansion and evolution. Ultimately, dark energy challenges us to think beyond static beginnings. It encourages a view of the universe as an evolving entity, one whose very fabric continues to unfold in surprising ways. As we delve deeper into the mysteries of dark energy, we find ourselves not just questioning how the universe began, but also how it will continue to transform in the eons to come. This ongoing narrative reminds us that the cosmos is not just a relic of the past, but a vibrant, ever-changing tapestry of existence. Zero-point energy is a fascinating concept in physics that highlights the mysteries of the quantum world. At its core, it refers to the energy that remains in a system even when it is at its lowest possible energy state, often described as the ground state. This energy emerges from the inherent characteristics of subatomic particles, which still possess fluctuations and movement due to the principles of quantum mechanics, even in a perfect vacuum. In discussions about nothing, zero-point energy challenges our traditional understanding of emptiness. We often think of nothing as the absence of everything, a void devoid of substance or activity. However, zero-point energy demonstrates that even in such a vacuum, there is a vibrant quantum dance of particles and fields. This realization suggests that nothing is not truly empty. Instead, it's a dynamic space filled with potential and possibility. This concept holds significant implications for various fields, including cosmology. For instance, zero-point energy relates to the fabric of the universe itself and even contours theories about dark energy. Some scientists propose that this elusive energy could drive the accelerated expansion of the universe, representing a critical component of our cosmos that remains enigmatic. Thus, zero-point energy serves as a bridge between the philosophical musings about nothingness and the rigorous demands of quantum physics. It opens intriguing discussions about the nature of reality, inviting us to reconsider what we think we know about the universe and the very essence of existence itself. In contemplating zero-point energy, we learn that even the void may hold secrets waiting to be uncovered. The interaction between energy and matter is foundational to understanding the processes of creation in our universe. At the most basic level, energy can transform into matter, and this relationship is beautifully encapsulated in the famous equation formulated by Albert Einstein: energy equals mass times the speed of light squared. This principle suggests that energy is not just abstract, it can shape the very fabric of reality, giving rise to solid objects and even entire stars. When we consider the earliest moments after the Big Bang, the universe was an incredibly hot soup of energy. As it expanded and cooled, energy began to condense into particles, first quarks and electrons, and eventually protons and neutrons. These particles formed the building blocks of matter, leading to the creation of atoms, which came together to form the stars and galaxies we see today. This transformation showcases a remarkable interplay where energy relinquishes its form to materialize into something tangible. Moreover, within stars, the fusion of lighter elements into heavier ones generates enormous amounts of energy. This process, known as nucleosynthesis, not only provides the energy that makes stars shine, but it also creates the elements essential for life. When stars reach the end of their life cycles, they explode in supernova events, scattering these elements across the cosmos. In this way, energy's transformation into matter enables the creation of new worlds, while the subsequent reactions within these stars initiate the birth of complex elements. This dynamic relationship between energy and matter continues to play a vital role in our universe. Whether in the quiet fusion inside a distant star or the energetic collisions within particle accelerators on Earth, these processes exemplify how energy and matter are entwined in the ongoing dance of creation. It's a reminder of the profound interconnectedness of all things in the cosmos, offering a glimpse into the very origins of existence itself. The question of matter's origins, especially the possibility of coming from nothing, has captivated scientists and philosophers alike for ages. Recently, groundbreaking discoveries in both quantum physics and cosmology have reshaped our understanding of this profound issue. One of the most compelling insights has come from quantum theory, which reveals that particles can spontaneously appear and disappear in what seems to be a vacuum. In these moments, it appears as though matter can arise from an absence of matter itself. This phenomenon challenges our traditional views of existence and brings into focus the role of uncertainty at the quantum level. In the realm of cosmology, the Big Bang theory has long served as the prevailing narrative for the universe's beginnings. New insights from observations of cosmic microwave background radiation have lent support to this idea, suggesting that the universe began as an incredibly dense and hot point. The expansion from that initial state has raised further questions about what preceded that inflation. Some scientists propose that the universe itself may have emerged from an earlier collapsed state, or from a vacuum that was unstable, supporting the notion that what we perceive as nothing may not be truly empty after all. Moreover, developments in string theory suggest that our universe may be just one of many, existing alongside others in a vast multiverse. If true, this idea further obscures the boundaries of nothing and something, implying that multiple universes might arise from a singular chaotic quantum state. This perspective implies that matter and energy are not the only entities in play. The very fabric of reality itself may facilitate the spontaneous emergence of universes. These scientific advancements have prompted a re-evaluation of an age-old question: can something indeed come from nothing? By integrating principles of quantum fluctuations, the creation of the universe, and the potential existence of a multiverse, modern science is painting a more complex picture of reality. In doing so, it opens doorways to philosophical inquiries that challenge our understanding of existence and the essence of nothingness. The story of matter's origins is far from settled, inviting us to ponder the mysteries of the cosmos as we continue our exploration of the universe's grand narrative. The concept of nothing, or the absence of anything, is not just a philosophical musing, but a fascinating area of inquiry in the realm of cosmology and physics. When scientists explore nothing, they often refer to the vacuum of space, a seemingly empty void that paradoxically is teeming with energy and potential. This emerging understanding reshapes how we perceive the universe and could profoundly influence future scientific research. For one, the study of nothing could lead researchers to better comprehend the origin and fate of the universe. Theories suggest that the universe began from an incredibly dense state, often described as a singularity, before expanding rapidly. By examining the conditions of nothingness that preceded the Big Bang, scientists may uncover answers to some of the deepest questions about the nature of existence itself. What existed before this nothingness? Can understanding it provide insight into the universe's ultimate destination? Furthermore, the properties of a vacuum are rich with surprises. Quantum field theory reveals that even empty space is filled with fluctuating energy fields, potentially leading to phenomena like virtual particles popping in and out of existence. This understanding not only challenges our concept of reality, but also opens pathways for ingenious technologies. Imagine harnessing this fluctuating energy for practical applications, from advancing energy generation to developing new materials for electronics. Lastly, the philosophical implications cannot be understated. Exploring the notion of nothingness might inspire a shift in how we think about existence, reality, and our place in the cosmos. As researchers continue to delve into these enigmatic questions, they could ignite interdisciplinary discussions that bridge science with philosophy, art, and even spirituality. Our exploration of nothing may ultimately illuminate not only the mechanics of the universe, but also deepen our understanding of what it means to be human in an almost unfathomably vast and mysterious cosmos. The relationship between nothing and everything in the cosmos is a profound mystery that has fascinated philosophers and scientists alike for centuries. One of the most potentially groundbreaking discoveries that could shine a light on this topic involves the nature of dark matter and dark energy. Observations have shown that around 95% of our universe is composed of these elusive entities, which seem to defy our traditional understanding of matter and energy. If we can decode what these components are and how they interact with the rest of the universe, we might uncover deeper insights into the very fabric that separates nothing from everything. Another exciting avenue of exploration lies in the realm of quantum physics, particularly the concept of quantum vacuum states. The idea that something can emerge from a state of nothingness challenges our intuitions about existence itself. If scientists can develop experiments that observe how particles spontaneously arise from quantum fluctuations, it would alter our comprehension of the universe's inception and evolution, suggesting a dynamic relationship where nothing can lead to something in unexpected ways. Further discoveries in cosmology, such as insights gleaned from the cosmic microwave background radiation, may also deepen our understanding. This faint glow, a remnant from the dawn of our universe, contains clues about its early state and expansion. By studying this radiation in finer detail, researchers could unlock secrets about how the universe transitioned from an incomprehensible void to the rich tapestry of galaxies, stars, and planets that populate our night sky today. Finally, advancements in theoretical physics, particularly in string theory and related models, could provide frameworks that link the existence of everything to nothing. These theories posit that the universe is made up of tiny, vibrating strings that can encapsulate the properties of particles and forces. By advancing our grasp of these foundational ideas, we may discover that the distinction between nothing and everything is less about opposites and more about a continuum of existence, inviting us to rethink what we truly know about the cosmos and our place within it. The quest for extraterrestrial life deeply intertwines with profound questions about our own origins. When we ponder how life could emerge in the vastness of the universe, we are also exploring the fundamental mysteries of existence itself. At the heart of these discussions lies the idea of origins from nothing, which challenges our understanding of how anything comes into being in the first place. The search for life beyond Earth often begins with the exploration of planets and moons within our solar system that could harbor conditions suitable for life. For instance, scientists have focused on locations like Mars and the icy moons of Jupiter and Saturn, such as Europa and Enceladus. These explorations might lead us to discover microbial life forms, which would be remarkably rich in implications. Such a discovery would not only expand our definition of life, but also open urgent questions about how life began in the universe and whether similar processes could spontaneously occur elsewhere. Now, when discussing origins from nothing, we touch on the scientific debates surrounding the Big Bang and the emergence of the universe itself. From a scientific perspective, the universe arose from an incredibly dense and hot state, expanding rapidly. Events that followed contributed to the formation of stars, galaxies, and ultimately the materials needed for life, combining elements like carbon, hydrogen, and oxygen into complex molecules. So, while the question of life's origins is often grounded in biological processes, it links back to physics and cosmology, leaping from minute cells to the grand cosmos. Searching for extraterrestrial life not only satiates our curiosity about the universe, but also forces us to reconsider our own place within it. It blurs the lines between biology and cosmology, challenging us to think about how life may arise from inanimate matter, and ultimately, how everything around us came into existence from what once was nothing. This profound inquiry captivates our minds and invites us to delve deeper into the mysteries of existence. Advancements in space exploration hold immense potential for enhancing our understanding of cosmic beginnings. As we push further into the cosmos, we gain access to environments and phenomena that can reveal the fundamental processes that shaped the universe. The early moments of our cosmos are obscured by time, but new technologies like advanced telescopes and robotic spacecraft allow us to peer deeper into the universe's past than ever before. They help capture glimpses of celestial objects formed just after the Big Bang, enabling scientists to study their composition and structure. Furthermore, missions to other celestial bodies within our solar system offer not only a perspective on their own histories, but also serve as analogues for the early Earth. By examining places like Mars or the moons of Jupiter and Saturn, researchers can gather vital clues about planetary formation and the conditions that may support life. For instance, uncovering signs of ancient water on Mars enriches our understanding of where and how life might emerge, both on our planet and elsewhere in the universe. Additionally, advancements such as gravitational wave detectors are providing new ways to explore the cosmos. These technologies allow us to detect cosmic events that were previously invisible, such as the collision of black holes or neutron stars. Observing these extraordinary phenomena helps scientists to understand the extreme conditions present in the early universe and offers insight into the fundamental forces that govern matter and space itself. Ultimately, our journey to explore the cosmos not only satisfies our curiosity about our origins, but also fosters a deeper appreciation for the interconnectedness of all matter in the universe. Each discovery leads to more questions, propelling us further into the mysteries of cosmic beginnings. As technology continues to evolve, so too will our understanding, bringing us closer to answering the profound questions about how it all began. The concept of nothingness intrigues philosophers and scientists alike, prompting deep questions about existence and reality. At its core, the philosophy of nothingness challenges individuals to reflect on what it means to have meaning and substance in life. As societies grapple with issues like existentialism and nihilism, these philosophies could profoundly shape future thought and development. For one, an emphasis on nothingness might encourage a shift toward minimalism in lifestyle. In an era characterized by consumerism and relentless pursuit of material goods, the idea of embracing emptiness could lead to a more contemplative society. Individuals might begin to prioritize experiences and relationships over possessions. This could foster deeper connections among people and promote a more sustainable way of living, as communities focus on what is essential rather than what is superfluous. Moreover, philosophies of nothingness could influence scientific inquiry. As we explore the vastness of the universe, from the tiniest particles to the infinite cosmos, the notion that everything emerges from a state of nothingness can spark new ideas in fields like cosmology and physics. Scientists may turn to this philosophical perspective to address fundamental questions about the origins of the universe or the nature of consciousness, leading to advancements that intertwine scientific understanding with philosophical exploration. Ultimately, as society becomes more aware of these philosophies, it may cultivate a sense of interconnectedness and humility. Recognizing that nothingness is a fundamental aspect of existence could lead to a deeper appreciation for life, encouraging individuals to seek purpose not in accumulation, but in connection, understanding, and continuous exploration. This transformative journey challenges us all to reconsider our place in the cosmos, allowing the idea of nothingness to inspire growth in thought and community for generations to come. Understanding the universe's transition from nothing has profound implications for how we view our own environment and the delicate balance of ecosystems on Earth. When astronomers and physicists explore concepts like the Big Bang and the origins of the universe, we confront the notion that everything we see around us emerged from an initial state of emptiness. This realization can shift our perspective on the importance of natural resources and the need for sustainable practices. The universe was once an incomprehensibly cold and empty space before it expanded, filling with matter and energy. This process invites us to reflect on our own place in the cosmos and consider the fragility of our planet. As we learn how complex structures, from galaxies to stars, arose from seemingly nothing, we are reminded that the Earth, our home, is a unique and precious product of such cosmic events. This recognition can inspire us to treat our environment with greater care, acknowledging that each component of our ecosystems has originated from the same cosmic beginnings. Moreover, understanding cosmic evolution emphasizes the significance of interconnectedness. Just as the universe functions as an intricate web of matter and forces, so too do the various elements of our environment depend on one another. This perspective encourages environmental stewardship, reinforcing the idea that actions taken in one part of the planet can ripple through ecosystems in ways we might not immediately see. The realization that we are part of a larger tapestry can motivate efforts to preserve biodiversity and protect natural habitats. Lastly, grappling with the origins of the universe compels us to confront existential questions about our role in the grand scheme of things. As we explore cosmic beginnings, we must also think about how our choices today shape the future of our planet. Each generation inherits the responsibility of not only understanding the universe's past, but also ensuring its future, adjoined with our Earth, remains sustainable and vibrant for generations yet to come. Our understanding of nothing has evolved significantly over the years, especially in the realms of cosmology and theoretical physics. Historically, nothing was often thought of simply as the absence of matter. However, modern physics presents a much more nuanced view. In quantum mechanics, for instance, nothing can still give rise to fluctuations and virtual particles that pop in and out of existence. This interpretation suggests that emptiness is not truly empty. It is a dynamic field full of potential. This understanding of nothingness has profound implications for theories about the fate of the universe. If nothing can somehow influence the fabric of reality, it changes our perspective on cosmic expansion and the ultimate fate of galaxies. Current theories posit that the universe is not just expanding, but accelerating in that expansion. This acceleration is attributed to dark energy, a mysterious force that constitutes about 70% of the universe. Some scientists speculate that dark energy might originate from the properties of nothingness itself. Another fascinating concept related to this idea is the possibility of a multiverse, a collection of many universes, each with different properties. Some theories propose that our universe emerged from a state of nothing, where quantum fluctuations triggered a Big Bang, creating our reality. If other universes exist, their interactions or the absence thereof could dictate the fate of our own universe, leading to scenarios like eternal inflation or eventual collapse. The modern understanding of nothing is not merely a philosophical query, but serves as a vital framework for contemplating the universe's fate. As we delve deeper into the nature of existence, we uncover layers of complexity that challenge our notions of reality and our place within it. The interplay between nothingness and existence continues to inspire questions about how the universe will evolve, urging us to look further into the cosmic mystery. Education plays a vital role in unraveling complex ideas about the origins of the universe and the concept of nothing. First and foremost, it serves as a bridge between sophisticated scientific theories and the inquisitive minds of learners. Without effective education, the abstract notions that populate cosmology can remain elusive, leaving people to grapple with vague concepts rather than fully grasping their significance. For instance, when discussing the beginning of the universe, particularly the Big Bang theory, education helps distill the fundamental ideas into relatable terms. It guides individuals through the transition from the notion of nothing, a state devoid of matter or energy, to the explosive, expansive birth of everything we see today. This transformative journey can be awe-inspiring, sparking curiosity and a deeper appreciation for the mysteries of the cosmos. Furthermore, education can demystify philosophical questions surrounding the idea of nothing. In classrooms or informal settings, educators can provoke thought on whether nothing can truly exist, or if it is merely a concept bound by human perception. This exploration encourages critical thinking and invites individuals to consider the interplay between science and philosophy, making complex ideas more accessible and engaging. Ultimately, equipping learners with a solid understanding of these profound concepts not only enhances their understanding of the universe, but also empowers them to engage in meaningful conversations. The role of education becomes not just a transmitter of information, but a catalyst for exploration and curiosity about the vast unknowns of our existence. Cross-disciplinary research allows scientists, philosophers, and artists from different fields to come together and explore fundamental concepts like nothingness and creation in fresh and profound ways. By merging perspectives, researchers can challenge each other's assumptions and uncover new angles on age-old questions. This collaboration cultivates a richer dialogue, enabling insights that might not surface within the confines of a single discipline. For instance, physicists studying the origins of the universe approach nothingness in the context of quantum mechanics. Their findings suggest that nothing is not merely an absence of substance, but may play an active role in the formation of matter and energy. Meanwhile, philosophers can frame questions about existence and non-existence, prompting scientists to consider the implications of their discoveries on our understanding of reality itself. Artists, too, contribute to this conversation by visualizing concepts that can be abstract or difficult to grasp. Through art, they can express the emotional and philosophical dimensions of nothingness and creation, inviting audiences to engage with these themes on a personal level. This artistic interpretation often leads to a deeper appreciation of the scientific principles at play, bridging the gap between analytical thought and human experience. Ultimately, cross-disciplinary collaboration enhances our perception of such profound themes. It nurtures a community wherein ideas flourish and evolve, shedding light on the complex relationship between nothingness and creation, showing us that these concepts are not just abstract thoughts, but essential elements of our universe's narrative. Together, they help us navigate the mysteries that continue to captivate our imaginations. Potential breakthroughs in theoretical physics can profoundly reshape our understanding of existence, inviting us to rethink not just the universe but our place within it. At the heart of these promising developments are theories like string theory, quantum gravity, and the unification of forces, which serve as frameworks to comprehend the fundamental nature of reality. These theories propose that what we observe as separate entities might actually be interconnected in a way that transcends our ordinary experience. For example, string theory suggests that what we think of as particles are actually tiny, vibrating strings of energy. This idea challenges long-standing viewpoints about matter and energy, implying that our universe is woven from a richer tapestry of dimensions and vibrations than we previously believed. If string theory, or any similar theoretical breakthrough, proves to be valid, it means our entire understanding of physical laws could shift dramatically, opening doors to new realms of scientific inquiry and philosophical reflection. Moreover, advancements in theoretical physics also raise profound questions about the nature of time and space. Concepts such as the fabric of space-time, which combines the three dimensions of space with time into a single continuum, invite us to contemplate the very structure of reality. Breakthroughs in our understanding of black holes, for instance, have illuminated ideas about information retention and the universe's fate, influencing our philosophical and existential musings about life and the cosmos. As we stand on the brink of these potential discoveries, we find ourselves at a crossroads of inquiry. Each new insight challenges us to reconsider long-held beliefs about existence. Are we mere observers in a passive universe, or active participants in a grand cosmic symphony? These questions extend beyond the confines of science and into the very essence of what it means to exist, encouraging thoughtful reflection on our relationship with the cosmos. Exploring how everything started from nothing invites us to consider the profound nature of existence itself. This inquiry is not merely about the origins of the universe, but prompts us to reflect on the very fabric of reality. It leads us to ponder questions about creation, the cosmos, and the laws of nature that govern our lives. Understanding this journey from emptiness to complexity offers a humbling perspective on humanity's place in the grand tapestry of existence. At the heart of this exploration lies the concept of cosmic evolution. From the Big Bang, which marked the beginning of time and space, to the formation of galaxies, stars, and planets, the universe has undergone a remarkable transformation. This narrative shifts our focus from the material to the potential, emphasizing how seemingly nothingness can give rise to extraordinary phenomena. It illustrates that the universe is in a constant state of change, evolving into more intricate forms over billions of years. Moreover, examining this journey from nothing encourages us to confront our curiosity and urge to seek knowledge. It highlights the remarkable human capacity for inquiry and understanding. As we delve into the mysteries of the cosmos, we find ourselves questioning not just how we got here, but also why we seek to understand our beginnings. This sense of wonder fuels scientific discovery and philosophical thought, bridging the realms of science and spirituality. The overarching message is one of connection and inspiration. By reflecting on how everything emerged from an initial state of nothingness, we recognize our shared cosmic heritage. This awareness fosters a sense of unity and responsibility as we navigate our existence. We begin to see ourselves as part of a grand narrative, one that instills hope and emphasizes the importance of continued exploration and understanding in our quest for knowledge about the universe and our place within it. The concept of creation from nothing, often referred to as ex nihilo, can spark profound reflection in our everyday lives. It suggests that new ideas or situations can emerge where there seemed to be nothing before. This perspective can empower individuals to recognize their ability to generate creativity and innovation, encouraging them to transform seemingly empty spaces into vibrant opportunities. In practical terms, think about how you might approach problem solving. When faced with a challenge, instead of seeing barriers, consider what new possibilities could arise. For instance, if someone is looking to start a new project, they can identify gaps in their own passions or in their community's needs. By conceptualizing these voids not as obstacles but as fertile ground for creation, individuals can initiate projects that contribute value and inspire others. Moreover, this approach can rejuvenate personal relationships. Individuals can apply the idea of creation from nothing by actively fostering connections or renewing friendships that may have gone stale. Something as simple as reaching out to an old friend or trying a new activity with family can lead to revitalized interactions and deeper bonds. It illustrates that relationships, much like ideas, can emerge anew with intention and open-mindedness. Ultimately, embracing the notion of creating from nothing encourages a mindset of possibility. It invites people to see their lives as a canvas where new experiences and connections can flourish. By recognizing that even in moments of emptiness, opportunities for growth and creativity exist, individuals can lead lives rich with exploration and innovation. The origins of the universe continue to baffle scientists, posing profound questions that demand further exploration. One of the most significant mysteries is the nature of dark matter and dark energy. Together, these two components constitute about 95% of the universe's total energy density. Yet we have yet to directly observe them or fully understand their roles. Are they merely different forms of matter and energy, or do they indicate new physics? Unraveling these secrets could reshape our understanding of the universe itself. Another lingering question is the state of the universe before the Big Bang. We often think of the Big Bang as the beginning, but that concept raises further inquiries. What was there before? Did time exist, or was the universe in a different form? Theoretical physics presents various models, but none has gained universal acceptance. This ambiguity invites speculation and fuels curiosity about the universe's true origins. Additionally, we are still grappling with the intricacies of cosmic inflation, the rapid expansion of the universe that occurred within the first fraction of a second after the Big Bang. While inflationary theory explains many aspects of the universe's structure, such as its uniformity, the precise mechanism driving this expansion remains elusive. Understanding inflation can provide insights not only into the early universe, but also into its ultimate fate. Lastly, the search for a comprehensive theory of quantum gravity stands as a monumental challenge. Merging general relativity, which governs the cosmos on a grand scale, with quantum mechanics, which rules at the smallest scales, is essential for a complete understanding. A unified theory could unveil insights about the fabric of space-time, and perhaps even explain phenomena occurring at the very dawn of the universe. These unresolved questions remind us that even with great strides in cosmology, the quest for knowledge remains open and far from complete. The narratives of beginnings, stories that emerge from nothing, offer a profound lens through which we can view human history. When we contemplate concepts like the Big Bang, we realize that even the universe started from a state of emptiness, evolving into the complex cosmos we inhabit today. This notion of creation from nothing extends beyond the fabric of the universe. It also resonates deeply with human experience. From the earliest hunter-gatherer societies emerging from primitive conditions, human civilization often flourished from seemingly barren origins. These stories reshape our understanding of progress and resilience. They remind us that monumental achievements can rise from humble beginnings. Just as stars are born in vast clouds of gas and dust, civilizations have often emerged after times of hardship and struggle. Think of the transformative power of human ingenuity. how societies can evolve from enclaves of isolated communities into sprawling metropolises. Recognizing that greatness can spring from adversity allows us to appreciate the trials faced by our ancestors as stepping stones to innovation. Moreover, exploring these narratives invites reflection on our place in the broader tapestry of existence. When we accept that the cosmos itself originated from a singular moment of creation, we find a mutual connection among all living beings. This perspective fosters a sense of unity, not just across cultures and time periods, but also linking humanity to the universe at large. It prompts questions about the meaning of life and our role in an ever-expanding universe. Lastly, these beginnings from nothing challenge us to reconsider how we can shape future narratives. If history teaches us anything, it is that opportunities arise from the unexpected. This idea empowers us to think boldly and create new paths, knowing that even from an absence of resources or clarity, novel and transformative ideas can take root. In a world constantly evolving, remembering our origins can inspire hope and creativity as we continue to navigate the complexities of human existence, striving to build a future that is even brighter than our past. The concept of everything originating from nothing is a profound idea that has intrigued various cultures throughout history. Many ancient philosophies and religions grappled with the notion of the universe's beginnings and the fabric of existence. In some Eastern philosophies, like certain strands of Buddhism, there is an emphasis on emptiness, known as sunyata. This idea suggests that everything is interconnected and that the essence of the universe is a kind of void from which all things arise. For those who embrace this perspective, the notion of creation from nothing becomes a pathway to understanding the transient nature of life and reality itself. Conversely, many Western religious traditions hold a more distinct creationist viewpoint. For instance, in Judeo-Christian belief, the universe is often viewed as the intentional result of a divine creator. The narrative found in the book of Genesis describes God creating the world ex nihilo, or from nothing. This perspective emphasizes purpose and intentionality behind the universe's existence, which contrasts starkly with ideas of random emergence from void or chaos. In these traditions, the concept of nothing as a source of everything can seem unsettling and undermining to the idea of a purposeful creation. Cultural attitudes can also shift and evolve as societies encounter scientific advancements. The theories of the Big Bang, for example, present a fascinating blend of creation from an initial singularity, challenging traditional views. In contemporary society, many have embraced a scientific understanding of the universe's origins that aligns more closely with the idea that everything might come from a state of extreme simplicity or even nothingness. This has led to deeper philosophical inquiries about existence, sparking dialogues that cross the lines between science and spirituality. In the end, how different cultures embrace or reject the idea of everything originating from nothing reveals much about their worldviews. From ancient texts to modern scientific theories, these perspectives shape how we understand our universe. Each culture provides a unique lens through which we can explore existence, consciousness, and the mysteries that persist in the heart of creation. Storytelling in documentaries serves as a powerful tool for conveying complex scientific ideas by framing these concepts within relatable narratives. When viewers are introduced to characters, whether they are scientists, researchers, or everyday people, it makes the abstract much more tangible. By weaving personal stories, triumphs, and struggles into the presentation of scientific ideas, the audience is not just absorbing facts, they are emotionally invested in the journey of discovery. Moreover, effective storytelling often employs analogies and metaphors that simplify intricate scientific principles. For instance, instead of merely stating the laws of physics, a documentary might illustrate these ideas through the experience of a child throwing a ball. This creates connections between personal experiences and seemingly distant scientific concepts, allowing viewers to visualize abstract ideas in a more comprehensible way. Visual elements play a crucial role too. Stunning imagery of celestial bodies, molecular structures, or ecological systems can captivate the audience while grounding complex ideas in visually striking representations. Such visuals, combined with a compelling narrative, can evoke wonder and curiosity, encouraging the audience to explore further. Engaging graphics that illustrate processes or transformations enhance understanding by providing a clear picture of what might otherwise be difficult to grasp. Finally, the pacing and delivery of the narrative are vital. A well-structured flow that builds excitement, suspense, or revelation keeps viewers on the edge of their seats. When scientific concepts are introduced gradually, allowing time for reflection and understanding, the audience is less likely to feel overwhelmed. Through storytelling techniques, documentaries can create an enriching experience that inspires curiosity and fosters a deeper appreciation for the wonders of science. Visual representation plays a crucial role in making abstract concepts, such as the idea of nothing, more comprehensible. When faced with the notion of nothingness, which can feel quite elusive, our minds often struggle to form a clear picture. However, visualization provides a mental anchor, allowing us to relate to these complex ideas in a tangible way. For instance, when we depict nothingness as a blank canvas or an empty space, it becomes easier to grasp, enabling us to move from a foggy notion to a more coherent understanding. Art, illustrations, and even digital representations can offer different perspectives on such abstract ideas. They serve to engage our imagination, helping to bridge the gap between our cognitive abilities and the intricacies of philosophical concepts. When an artist creates a visual encapsulation of nothing, they often provoke thought and invite viewers to contemplate deeper meanings. This visual stimulus can ignite discussions and reflections, enhancing our intellectual engagement with the topic. Furthermore, in fields like cosmology, visual aids are instrumental in explaining complex phenomena. For instance, scientists might use simulations or models to represent the vacuum of space, emphasizing its vast emptiness. With visuals, we can witness interactions and movements that help solidify our understanding of emptiness, contrasting it against the backdrop of the universe filled with stars and galaxies. These representations not only simplify the learning process, but also expand our capacity for imagining concepts that defy our everyday experiences. Ultimately, visual representation transforms the abstract into the relatable. It allows us to be more curious and inspired by ideas like nothingness, encouraging a richer dialogue and deeper exploration of what it means to exist or not exist in the cosmos. By tapping into our visual literacy, we become better equipped to handle the philosophical and scientific complexities that lie beneath the surface of seemingly simple ideas. Engaging in discussions about nothing may seem counterintuitive, yet such conversations can spark profound creativity in both the arts and sciences. By exploring the concept of nothing, artists and scientists alike are prompted to consider the absence of defined forms and ideas. This blank slate enables them to challenge existing norms and conventions. It allows for a departure from traditional thinking, providing fertile ground for new and innovative concepts to emerge. Take, for example, the minimalist art movement. Artists embraced simplicity, stripping their work down to essential elements and exploring the beauty inherent in emptiness. The conversation around nothingness prompted them to reconsider what art could be. It encouraged a focus on the viewer's experience and interpretations, emphasizing the idea that meaning can be found in the spaces between things, and sometimes even in nothing itself. This shift in perspective is vital, as it opens the door to new styles and expressions that honor absence as much as presence. In the world of science, the concept of nothing is just as intriguing. Scientists grapple with the idea of a vacuum, a space devoid of matter. This exploration has led to groundbreaking theories, especially in fields like quantum mechanics. It turns out that what we think of as nothing can actually be teeming with potential, where particles pop in and out of existence. Such discussions encourage scientists to rethink foundational ideas, leading to new theories that challenge our understanding of the universe. Ultimately, talking about nothing underscores the importance of absence in fostering creativity. It provokes thought, leading to unexpected insights and breakthroughs across various disciplines. When we allow our minds to wander through the emptiness of nothing, we often discover the richest ideas hidden within that silence, illuminating the path toward innovation in both the arts and sciences. The concept of nothing might seem abstract or even trivial, but it holds profound significance in our exploration of existence and reality. Philosophers and scientists alike have long grappled with the idea of nothingness, often translating it into broader existential questions about our purpose, the nature of the universe and what it means to be. When we ponder the void, we inevitably confront ideas about creation, destruction, and the very fabric of reality that shapes our understanding of life itself. Historically, many philosophical traditions have questioned whether true nothingness can even exist. For instance, in physics, the vacuum of space, once thought to be emptiness, is now understood to teem with potential and energy. This challenges our interpretations of nothingness, suggesting it is a state full of possibilities. This shift in perspective helps bridge the gap between scientific inquiry and existential pondering, showing us that what appears empty might be full of hidden meanings and possibilities awaiting discovery. Further, the journey of understanding nothingness leads us to reflect on our place in the cosmos. If nothing can give birth to something, we can start to appreciate our own existence as a remarkable occurrence in a vast and seemingly indifferent universe. It raises questions about destiny and chance, urging us to explore the interconnectedness of all things and how even the smallest actions can ripple through the fabric of reality. This interconnectedness can evoke a sense of awe and wonder about life, inviting us to reconsider our roles within the greater tapestry of the universe. Ultimately, contemplating nothingness pushes us to examine our beliefs, our existence, and the universe around us. It challenges us to look deeper, confront our fears about the unknown, and question what it means to exist at all. By embracing this journey, we enrich our understanding of both the cosmos and ourselves, revealing a complex relationship between the void and the vibrant reality we inhabit. When we contemplate how everything originated from nothing, we delve into profound questions about existence and our place in the cosmos. This reflection often stirs a call to action that encourages us to appreciate the rare and precious nature of our reality. After all, the universe, with its immense scale and intricate design, began from an enigmatic event known as the Big Bang. The transformation from nothingness to a universe teeming with galaxies, stars, and planets invites us to marvel at the extraordinary journey of existence. This understanding can inspire a sense of responsibility toward our planet and each other. Recognizing that we are remnants of cosmic history can encourage us to become stewards of the Earth. It highlights the need for environmental awareness and sustainable practices, as the universe has provided us with a fragile oasis amidst the vastness of space. Therefore, protecting our home becomes a collective mission, for it is not just a matter of survival, it is a tribute to the cosmic origins that brought us here. Moreover, contemplating our cosmic beginnings sparks curiosity and a thirst for knowledge. It inspires us to pursue science and encourage future generations to do the same. By seeking to understand the forces that shaped our universe, we can learn more about ourselves and our potential. This quest for knowledge can empower us to innovate, create, and explore, bridging the gap between past and future. Ultimately, reflecting on how everything started from nothing leads us to a call for unity and understanding. It serves as a reminder that despite our differences, we share a common origin and a collective journey. As we ponder our existence, we can take action by fostering connections, embracing diversity, and working together to navigate the challenges that lie ahead in our shared universe.